Alright, hell yeah. So we have physics, and we're going to do something we usually don't do. We're just going to go over this problem, hopefully in about 5 minutes. So we have a basketball player, shoots a basket 10 meters out. Now, a three-point line is 7.24. We'll go over that after this. So it's a far 3. And so anyway, 2 meters tall for the height of the throw, and 3.05 for the height of the basket. 40-degree angle, and then let's go for it. So typically these equations have you're looking for like a couple equations, couple unknowns, and continuity too. So we know that there is no gravity sideways, there's no forces on the basketball sideways. Velocity is constant in this direction. So our first equation right off the bat is if we knew the time it took from the throw to the basket, well, that time times that velocity is 10 meters. So that's the first equation. Hell yeah. And then we know some components about we want to know this velocity. But we know, hey, this component Vx is that velocity cosine 40. You know what I mean? And so that's this equation. So that's technically the equation, one of the equations for our two equations, two unknowns. Now, the second equation comes from the fact that we do have some velocity up, but we have gravity, you know what I mean, sucking that right up. So acceleration is negative 9.8. What the hell is that? It's negative 9.8 meters per second. That's the change in velocity every second. So booyah. Within a fraction of a second, that it takes about a second to get here. Let's just say that. So in half a second, that velocity is gone, and then it goes back the other way. Okay. But what we do is we integrate this. We know that A is dv dt. We separate variables, we integrate, so we get v is equal to negative 9.8t plus, but we need a constant here. So you do this by putting in, at t is equal to 0, well, do we have velocity? Hell yeah, we have velocity, and it's that vy. And then you integrate again, because v is dy dt, y is this case, it's the distance in the vertical. And so we have dy dt, separate variables, we'll have dy over here, and then throw the dt over there, integrate, you get, half the acceleration, t squared, plus that initial velocity times t, plus, and here, so at time is equal to 0, these go to 0, what's our height? It's 2 meters, so we throw that in. Hell yeah, so that's our equation. And then we want continuity between these. So what we're going to do is pick the time t to get here. So at time t, that's t final, but I just call it t. So at that time t, well, we're going to go a distance of 10. So this equation is 10, and we got that v cosine 40 t. Now this equation, at t is equal to that t final, what's going to happen for y? It's going to go up, but then come back down to the 3.05. You know what I mean? So then you have that. And we basically have two equations. The two unknowns are t and v. But we just want the equation for v. So if you're smart, you turn this equation in a function of t and then jam it in there. And then you just got one equation with v. So that's what we do. We rearrange this. We get t is 10 divided by that v cosine 40. We also want to square it just because we have to toss this t into that square sign, and so we do square it, and then we just throw it in. So we have 3.05, 4.9, that t squared term, plus v, and we have sine 40, and then t. Well, we have divided by a cosine 40, and divided by a v, and multiplied by 10. So we have v divided by v, those cancel. We have sine 40 divided by cosine 40, it just turns into tangent 40, and then multiplied by 10. So at the end of the day, this is just tangent, or 10 tan 40, 10 tan 40, plus 2. So these are constants, we get these to over there, so we got that. And now we have it equal to this. Our v squared is downstairs, this is what we want, so we kind of do it all in one step. We take our v squared upstairs, and we take this, and then we shove it within a parentheses right downstairs, right where that v squared was. And then we take the whole square root of it, and then we get something v is the square root of all this. Cool. And now for our problem, it's just numbers, but hell yeah. And so we get a velocity of 10.67 and a time of 1.22. So keep that in mind because we have 10 meters out, it takes 1.22 seconds. We need a velocity of 10.67. Now that's meters per second. 10.67 times 2.25 gets us pretty close. 24 miles an hour for basketball. Now, what I wanted, I wasn't satisfied enough. I wanted to get this back into letters. So what we did is we said, well, negative 4.9 is just the acceleration divided by 2. That's negative 9.8 divided by 2. So we got a divided by 2. This 10 is this distance. So that's just distance away from the basket. And then this is our final height. And so we can get back down here. This is our final height right there. Minus our initial height, so y initial. Minus the distance again, tangent of the angle. And then cosine squared of the angle. Okay, hell yeah. So then now we have an equation for velocity. So at any given angle that I shoot, and knowing the distance away I'm at, I can know, and my height of shooting and the basket's height should be, for an NBA player, that shouldn't change too much. And this is identical. This might change how far you are, how big of a three you're shooting, and you get an equation for velocity. But this equation isn't the best because basically, I was doing this on YouTube, watching Stephen Curry shoot, threes, and what I noticed was like, hey, he's at the three-point line, and so I know from NBA that's 7.24. So we do something like this. We know that he's shooting at 7.24 meters. Because it's YouTube, I can clip it, and then I threw it into my video editing software and just really made sure the time was correct. And so I got like 1.06 seconds so at the three-pointer, the shortest time was 1.06 seconds with an angle of 42.2 degrees. But let's take a pause, because what I want was to get this in terms of just an equation for angle. I wanted to go to a YouTube video, and then, angle is what I want to know, but I want to go to the YouTube video, see how far they are away from the basket. Sometimes they're farther. And then know the time, and I can do that by clipping the YouTube, like I said. I know the acceleration, that doesn't change. And then typically the height of the basketball player and the height of those aren't going to change. NBA basketball players 1.83 meters on average, and then plus their arm height. So 2 meters is a pretty good estimate. Okay, hell yeah. So when we do this, we can clip videos of basketball players shooting threes, and I just did Stephen Curry for a few. Because I wasn't satisfied. And you'll see later in this video, I made a huge mistake. I clipped one clip from Curry, and the YouTube, I just went on YouTube, and then just saw how long the time was, and usually frame by frame, I thought was accurate. Hell no. And so I got a time of 1.5 seconds, and so that was wrong. That one came out, and when I put it into Wondershare as a normal video, it turned out to only be 1.1 second. And so even that long, deep three had an angle of 37.6. But now I don't trust either of my YouTube. If YouTube I thought was accurate and said one thing, and YouTube should have been accurate, you know what I mean? Like, you're watching a video in real time, hopefully it didn't get any weirdness. But then I clipped it, but yeah, so maybe these aren't right. But anyway, it's just like, I'll have to do my due diligence later. But this video, I do my analysis on 1.5 second and then I said the shot was 10.5 meters, but 9.07 is more accurate, and we'll watch those clips. Because it's 6 feet away. I figure, hey, it looks like 6 feet away for that initial shot. But if the time frame is right at 1.1 second, it's 37.6. But if the time frame is wrong, you know what I mean? We have this in our calculator, 9.07 and a time of 1.1. Whoa. Not 9.07. Why the hell is that messing up right now? No. Alright, hell yeah. And before I forget, how do we get this equation into an equation for angle? So the first thing we're going to do is like square V. Got it. But what is V? We go back to that equation, 10 times the velocity in the x direction times t You know what I mean? And how do we get it in form of v? Well, it's 10 v cosine 40t. So we're going to get, just isolate the v. That's 10 divided by cosine theta t. We got to square it, so then we get that. And now this term, you know what I mean, we can just substitute in. And we can see that this is d squared divided by cosine theta squared times time squared. And when we throw it in this side, you know, the square root goes to the square, and we already squared it. Cool. We have a d squared and a d squared. Those cancel. We have a cosine squared theta and a cosine squared theta. Those cancel. So now we're just on a roll. We have 1 divided by t squared. So what I'm going to do is bring the t squared. What the hell do I do? Well, no, I guess I just go 1 divided by t squared. We have that area divided by 2, and then we have this. Now, to get closer, to get this angle out, let's see. Oh, I probably do this. Yep. So I bring this upstairs to the left, and then I bring this t squared up there. So hell yeah, I get to here, and then I rearrange. I add this d tan theta over there, and then I subtract this over here. Heck yeah. And then I just flip-flop the equation. That's what I do right there. And then I just divide by d. But all this in the parenthesis, now inverse tan is the angle. And now I have a function for the angle where I can just throw the distance away from the basket, the time it takes a shot to be made, and then the initial height of a basketball player, and then the height of the rim. Okay, hell yeah, let's get on with it. All right, we're back. It was just kind of getting bugged up in my calculator, but hell yeah, we got it all crispy. And so we have this equation, you know what I mean, and then we plug in those parameters. For that long 3, it was 37.6. So I think the take-home message is if you are farther out, you're probably going to do a shorter angle. You know, after I was running, you know, you'll see in the video, I was just not, I was thinking it was, you know, is this problem wrong? Are most all 3s taken from a 45 to a 50 degree angle? But my time was off. But like I said, I really don't know. I'll have to watch an NBA game and then actually clock some of the 3s for me to be confident. Because even a recording, I just can't trust it. And I clipped it up. And you know, the fact that I'm getting a different time just from YouTube and then clipping it out and putting it into a video editing software, that's the part that's not 100%. But at the end of the day, sure, you know, people are shooting between 40 and 50 degrees, you know, 40 and 48. So that's what I got. And if they're really close to the 3-point line, you know, here was the times, and I think the angles go up because you're probably shooting up over players. But anyway, like, I'm hoping that this video editing software was a better time frame for that, because it shows the exact time frame. And so hopefully I'm right about these 42, 44, 45 for the actual arc length of a basketball. Else I'll just have to make this video over again, and we can do that. But hell yeah, so that's it. That's this problem in a nutshell. And now we're going to watch some of these clips. And yeah, you know what I mean. It's not the best, but we'll at least go through all those clips, all 4 of these in a row, this order, so then you can make your own assessments. But this first clip, I'll show you the mess up, and then I'll show this one. So I messed it up at 1.5, but anyway, you know, you be the judge, and then we'll just go into the normal video. It's hella long because we learn a lot of stuff about integration, and we do it like we usually do it. But there you go. You know what I mean? That's the whole problem in a nutshell. And thanks for joining me. And
Brooks get him right back. And steps. Brooks get him right back. And steps. Clark came out nicely. Now the step back 3 is good. Tatum's 22, Brown 24. Both turnovers now for Boston. Curry catches, fires, scores.
And hell yeah. Alright, hell yeah. So we have physics, and physics sucks, man. You know what I mean? You know, trains go in 2 different directions. Every physics problem should just be solved, and everyone should just cheat their way through, you know what I mean, the first 2 semesters of physics. So that's what we're doing, you know what I mean? We're explaining physics problems because they're brutal, and it seems like they shouldn't be. And so typically what you're given is like, hey, we're throwing a basketball with some sort of velocity, and then like how far does it go? But this one's a blue problem. It's like 2-star. It's medium difficulty because we're not given the velocity. So we're saying, hey, if we shoot the basket from here to here, you know what I mean? What's the question? Sometimes I don't read, I just go to the question. So what is the initial, they want to know the velocity that it comes out of your hand. So now we're going to go from right here is like, well, we'll just go to YouTube. Let's watch, I think this is Seth Curry. And so let's see how long it takes him to shoot a 10-meter. Now, I had to look this up. So the 3-point line is 7.5, or somewhere in the sevens. 7 in between 7 to 8 meters is the 3-point line. If you're standing behind it, so you have to be another 6 feet out. So keep that in mind. In the video, you might have to watch it twice. Is Seth Curry 6 feet out? Well, maybe not, but we'll see. I gotta. And the cool thing about YouTube is you can stop frame it. Or use like the period. I think the period and then the comma key is like go forward 1 frame. And this is a 60 frame per second video, and it was 90 frames basically from get to there, minus a couple frames. But hell yeah, so that would be 1.5 seconds, and let's roll the clip. All right, so we're back, I guess, and so hell yeah, so it took 1.5 seconds, and so then what do we do with that? Well, so you do have vectors here. So if you're shooting it at a 45-degree angle, let's say we're just shooting at let's say we're just shooting at a 45. You know what I mean? Or forget that. Let's just say we're passing the ball this way. And it takes 1.5 seconds to get from there to there. You know what I mean? So let's do the easier problem first. So if it takes 1.5 seconds to just shoot a basketball straight across 10 meters, well, what's the definition of speed? You know what I mean? And let's go back to this. So speed is change in position, change in time. You should always write it like this. Same with acceleration. Change in velocity, change in time. Because now it's an equation. We got 3 things that we can input. We just found the change in time. We want to know what? We want to know the velocity. But we do know the change in difference. So it's 10 meters. So if we just threw the basketball 1.5 seconds to get from there to there, we would have 10 meters in 1.5 seconds. And I have to use my calculator. And we get 6. If it only took 1 second, it would be 10 meters per second. But it's less than that, so it's 6.7 meters per second. No one knows what that is because I live in America. Anyway, so I just do this. Multiply by 2. That gets you there, but 2.25, for whatever reason, I call it a 25% tip. That's how I remember 2.25. You know what I mean? So 6.2 times 2.25. Oh, sorry. 6.7 times 2.25. This thing's going 15 miles per hour if you're just shooting straight across. Now, do we have to have a higher velocity if we do like an arc? To get to here, and it might not be too intuitive, but yes. And let's say we just shot straight up in the air. Would we ever get to this point? No. But let's say we just shot with like a 1-degree angle. You know what I mean? At a 0-degree angle, we would have never got to the basket. At a 1-degree angle, would we get to the basket? Sure, but wouldn't you just have to almost shoot to the moon and then come back out? So wouldn't that take a longer time? Sure. So if it takes, and now even I'm tripping myself up. Yeah, so if it takes a hella long time to get here, the velocity this way from there to there is really slow. So this brings up the concept of you have to know that you have kind of 2 different components for velocity. You have the velocity in this direction, and then you have the velocity in this direction. So when you do a 40-degree angle, let's say you did a 45, and let's say your velocity was 10 meters per second, and this was 45. Well, you know that these two are the same, and you could use, easiest thing to do is sines and cosines. I like to do hey, this is the angle, sun is shining. So this is the sine part, that means this is the cosine part. What that means is that, you know what I mean? If you take this longer distance, bigger number, bigger number times the sine of the angle, that's going to give you this length. And, you know, sine of an angle and then cosine of the angle, same thing here, bigger number times cosine. These are always smaller numbers than 1. They're always 0 to 1. So it's a fraction of this. This is always the largest number, and then these components are always going to be smaller or equal to if your angle's like 0, that way, hey, 0 angle. The cosine component's the same as the hypotenuse. You have no sine component. Or if it's totally vertical, hell yeah. Your angle is literally 90. You know what I mean? Your sine components, everything, and then your cosine components, like nothing. That's hard to visualize. So let's just say our angle is how do we do like a 7-degree angle? It would look like that. Okay, so our sine components getting real big, cosine components basically going away. And this angle right here is approaching 90. It's like, you know, 99, 80, 85, 86, 87, 89. And then that booyah, that angle is 90. We have no cosine component. So it's just good to go over that. The other way, just know that you can always use Pythagorean theorem. You know what I mean? There's plenty of problems where you're just like kind of overthinking. You don't even think Pythagorean so this is your c squared, a squared, b squared. A squared and b squared are the same, but let's just do a squared plus b squared is equal to c squared. These two are the same, so we can go a squared plus a squared is equal to c squared. And we can do 2a squared is equal to c squared. We can throw in the 10 right now, so that's 2a squared is equal to 100. Sometimes it's easier mentally to do that. Now we can say, hey, this is a squared is 50. So now we have a is the square root of 50. Now if you don't know what the hell this is, well, square root of 64 is 8, and then the square root, what's the square root of 7? 49. Oh, sweet. So this is really going to be like really close to 7. And, you know what I mean, just intuitively, there's a few sines and cosines you should know. Obviously 45, it's sine of 45 is 0.707. So multiplied by 10, you got 7.07. And I just remember 007 for this, you know what I mean? And if you think 007, hell yeah, because you can't go wrong, because it's not going to be 007. That'd be ridiculous. And I don't think it would be 0.700, because why the hell would you even do 2 zeros at the end? It would just be 0.7 at that point. So 0.707, think 007, and I don't know. But that's the way I do it. Anyway, so hell yeah. So we're just saying that our velocity is going to be hella, and then we have components upward and this way. And if we're at a 45-degree angle, these components are the same. Same velocity sideways, same velocity up. Now at a 40-degree angle, well, look at that. You know what I mean? Just visually, this looks larger, this looks shorter. So we have more velocity this direction and less velocity that direction. Okay, so here's our velocity initial. It's going to have a velocity initial. This is our angle. So now if we want to get technical, this is the sine component. Velocity initial times the sine of the angle. See, but you know, if you're doing physics, you know, watching physics lectures, and you're just not up to speed on your sines and cosines, but you still want to watch the lecture, you know, once they get to here, you're like, nah, I lost you, but now you're not lost. And then you know this component's, you know, especially even high up physics, you know, they're not going to spoon feed you sines and cosines no more. But I will. Okay, so we got velocity initial cosine component. So there you go. Now hell yeah. And we can put labels on this. This is the velocity in the y direction, vi sine theta, and the velocity in the x direction is v initial, whatever that's going to be. That's kind of what we're solving for, cosine theta. Now, from the Seth Curry video, we already know that change in time is about 1.5 seconds for this. You know what I mean? And what do we know about... well, see, this is where I totally break it down. Hey, this basketball is a mass, and guess what? We're putting a velocity on it. Now, what we do in a lot of different things... You know what I mean? The first thing that we do is like a free body diagram. So what I like to do is chop it out of space. You know what I mean? So what we're going to do is just chop it and then just pretend it's in outer space. And so what do we know about it? Visually, we know that it has a velocity. Cool. Well, just pretend it's in the deepest part of space ever. If it has a velocity, and that's all we know, well, what's going to happen? If it's just in space, it's just going to go that direction forever. You know what I mean? So that's the definition. This is F equals ma. You have to go back to it. You know what I mean? This is why you signed up for this. Anyway, and but then because there's two scenarios. If the velocity is 0, it also is just Newton's law. Just say, hey, it's just going to stay there. You know what I mean? And if it's in deep space, it must just be like floating and hovering. You know what I mean? So this brings up the next thing, is that we know that it's not in deep space. Oh, damn it! You know, we have to go back to the. Sometimes this works for statics. I'm trying to apply it to this problem. So you have this equation that says F equals ma. Here is your mass, and we want to observe if it has acceleration. In this case, let's say we don't know. You know what I mean? We're gonna throw the question mark. We don't know because if we identify a velocity, it might not have acceleration. It might just be going that direction forever. But then we go to what do we observe? Well, we observe that this thing has an initial velocity, and then well, this is tricky. I mean, let's say you threw the basketball straight up and then straight down. You would throw it up with an initial velocity. It would get to the top. You would call that velocity 0 at the top of the arc. I mean, or just if you're just throwing it straight up and straight down, velocity would be 0 right there. So you would observe a change in velocity. That's what you're going for. Over on this side of the equation, you're trying to observe an acceleration. You know what I mean? And if you can do that, cool. You know, that gives you information. And you can do the same thing over here, and you can actually get the same result you were trying to observe. So in this case, because we can't just hand wave it. Like, I guess the hand waving part is like, hey, the velocity component this way doesn't change, but you want to know why. You know what I mean? That's the question. You want to know why the velocity in this direction doesn't change, but the velocity when you throw it up changes. Well, it has everything to do with this side of the equation. So now let's just take the basketball being thrown straight up and straight down, or and the second, well, we're going to observe right here. We're going to say, hey, this thing was thrown. It's no longer touching the basketball player's hands. We're going to do the free body diagram, chop it out of space. In this scenario where it goes straight up and down, we're going to say, hey, we have a velocity. But that's all we know. You know what I mean? So if we chop this out of space and we put it into deep space, for all we know, it's just going to go that way forever. And so I like to consider kind of this side of the equation, the motion side. And you want to be like, hey, do we observe motion? And even velocity is a check mark. It's not a check mark for acceleration. Don't get that confused. Because velocity 0 and velocity initial, these two scenarios could be the same where your acceleration is still 0. You know what I mean? But you know, we at least observe some motion, so check mark. That's all we know right now, is that we have a velocity. So now we go to this side of the equation. Now this side of the equation can be real simple, because if we do have a mass, well, hell yeah, you're no longer on the outskirts of every galaxy. You're probably on planet Earth, and guess what? We have a huge Earth underneath us. So if you are doing an analysis on a mass like a basketball, well, you have this Earth underneath you, and so the equation is Kepler. You know what I mean? It says, hey, there's a distance between this basketball and the center of the Earth. Both have a mass. This is mass Earth. This is mass basketball. And then we have Kepler's equation that says, hey, the force between these that they're pulling, attracting these two objects, is gravitational constant, m1 me. You know what I mean? Divided by r, the radius between them, which for all purposes is just the radius of the Earth. No one cares that is the radius of the Earth plus the height of the basketball players, fully stretched out arms. No, you know what I mean? That's potatoes compared to the radius of the Earth. It doesn't even matter if that basketball player is on Everest compared to sea level. Your answer is pretty much going to be the exact same. You know, it'll be slightly different, but like indistinguishable probably. Okay, so if you take so that's the force, and if you just, because sometimes you do this in a box and then you find the gravitational constant, which is this G-R-E-M-E, but don't, you know what I mean? You can rearrange this, because usually they say the force is equal to the weight of the object, which is mg. So where the hell does that come from? Well, the g part is everything I just circled. So now the mg is just this m times that g. You know what I mean? So hell yeah. So if we do have a mass, you know, and we're near the Earth, you do this. You put a weight on it of mg, and you have identified your first force. You know what I mean? And if you identify a first force, you know what I mean? Hell yeah. Go back to the motion equation and be like, well, is it stationary? Is the velocity 0? Because that indicates helistatics. You know what I mean? That if you identify a force because you have mass, and you identify that there's 0 velocity, well, you have identified one force, and for, you know what I mean, it has to have a other force that balances it. Usually the normal force, because it's like, you know, attached to the basketball player's hands, it's on the basketball court, but in this case we don't. You know what I mean? We have total air around this basketball. So we're done with the forces. So now that's it. That is the only force on here. So now we go back to our F equals ma equation and say, what the hell does that mean? So we have a force is equal to mass times acceleration. So now this is the tricky part, you know what I mean? Like, what side do you put them in? Because this almost looks like mg over here. But this is the biggest hiccup, like, of trying to use the F equals ma. Is like, no. You've identified the force, and due to literature, you know what I mean, of all the greats before you, they have figured out what the relationships between some of these forces in the universe are. And over here is the G-M1-M-E divided by the radius of the Earth, squared. And then that's going to be equal to your M1 mass of your basketball times your acceleration. Okay, so now you do have an equation that's F, this is the force side, and this is the motion side. And if you wanted to just find the motion, the acceleration, well, then you would divide by this mass. You know, take this mass downstairs, great, both masses cancel. So now you have an equation that's just for the motion. You know what I mean? You have acceleration is g, mass of the basketball, radius of the Earth squared. And am I missing a term? G M1 ME. No, because it was just, yeah. This term right here is gravity. You know what I mean? So cool. If you type in, and this is 6.67, just, you know, times 10 to the negative 11, mass of the basketball. Wait, do we even know the mass of basketball? I guess not. Oh, where the hell? Sorry, I totally apologize. See, we already crossed out the mass of the basketball. My letters are getting so tiny. This is the mass of the Earth. I'm sorry if I actually said it was the mass of the basketball right there. No. This M is the mass that we're trying to identify or do something with. So hell yeah. So this is gravitational constant mass of the Earth. That's like 5.94 times 10 to the 24. Good one to remember. And then mass of the Earth, radius of the Earth is 6 point, you can just say 6 times 6 to the 6. You know what I mean? Is 6 million. 6 times 10 to the 6 million. But I think it's like 6. Is it 6.37? I got it in my calculator still. Yeah, 6.37. It's just good to get used to memorizing some of these values. So 6.37 times 10 to the 6. That's 370,000 meters. Cool, but at the end of the day, this is just acceleration gravity 9.81. You know what I mean? Meters per second squared. All right, hell yeah. So now we know that I guess we know that we have an all right, hell yeah. So if we have this, we know that we have an acceleration, and if this force is down, you know, how do we figure out what, you know, we have to put, you know, let's say this is the positive y, this is the positive x, and we just said that we had a force down, so like obviously this should be oh, and this is the bummer when you're just like, well, if I already put the arrow down, does that mean it's so let's do it. The force. So and this force equation, well, we're just worried about the y. So we're saying the forces in the y is equal to mass times the acceleration in the y. We're just doing the problem of the ball goes up and down. We could care less if it goes sideways. And so we have a force that's down. So that's going to be negative mg is equal to may. So the m's cancel, and we have the acceleration in the y direction is negative g. Cool. All right, hell yeah. Oh, and I get it. You know what I mean? Because this is W, and we know W is just mg, but it's in this direction. So we could say, you know, if we already chose this direction, and this is our term W, well, we say it's still oh man, I don't want to confuse myself. It's just like, well, why the hell get confused over something simple? I'd need to make a whole nother video on just like how not to get confused. Like, you know, if you said if the weight was negative mg, that means our arrow's going the wrong direction. That means our arrow is actually up, and that's what that would mean. You know what I mean? So then, you know, if there was an acceleration up for whatever reason, you know, I mean, the Earth was up in the sky or something, then you know, then your force is still in the downward direction, and we would still go negative W is equal to may. But how would we get but W would be negative mg, so we would get negative mg is equal to may, and then you would get ay is equal to g. So if the Earth was above, and then I'm just working on sign convention, that was dumb, but at least I think that explained it. But anyway, so the force is down. We're saying this direction is the negative direction. That was this negative, and then we just throw in W. So again, it's negative W is equal to mass times acceleration in the y. That's what we did. And then we found out the acceleration is negative g. Okay, cool. So now what the hell do you do with this? Because that was the other thing, is like, at this point you can take it to Excel. This is exactly what I wanted to do. But this problem isn't conducive to it because we don't have a velocity to use. You know what I mean? If it said, hey, we're going to throw this at 10 meters per second straight up, you know what I mean? Then you can take this to Excel. So we might take a little break and then go to Excel, because the best thing to do is know that acceleration is an equation, even though you just got like a number for it. This is going to happen all the time because of gravity and things in free fall with these problems. Yeah, your acceleration is constant. But it's still part of an equation that says acceleration is change in velocity, change in time. So if we set this up in Excel, and we're just going to say our velocity initial is 10 meters per second straight up, what we would do is we would say, then you need to do, the first thing to do in Excel is do time. And then, you know, let's go 0.1 seconds, 0.2. And most all these problems with velocity, with projectiles, anything you're throwing up that comes back to the Earth, I mean, unless you're like going off a huge bridge, like a huge dam, like maybe 5 seconds for that. But every problem, that's a check on reality. Every problem will be like, you know, throw something up and have it come back down, usually less than 5 seconds. And in this case, hell yeah, it was just 1.5 seconds. So we're gonna throw this ball up at 10 meters per second, and well, let's do this. Let's at least, because one of the things is I wanted to get kind of close. I wanted to use that Seth Curry example that the change in time was 1.5 seconds. And we don't need to go, so Blue's Clues on explaining everything. What this means, and if you just take my word for it, that there, well, let's do it. So if we have that basketball, there is no forces this direction. So if we do have a velocity component, it's kind of like separating the problem. Now we do have a velocity this way. Cool. We have F equals ma. And this is in the x direction, acceleration in the x direction, and we have velocity in the x direction. Well, if this is in deep space, outer space, and we have a velocity going that way, it's going to keep going that way. And the wild thing is it does. It obeys that principle. The basketball feels like it's in deep space, and it's going that way, and it wants to keep going that way. There is absolutely no forces on this basketball in this direction. And I find that absolutely fantastic. So you can take the analogy that this thing's induced. It's just going to go that direction forever. The only reason why it stops going that direction, two things, well, air resistance, you could say that, but no, it's because it'll just hit the earth. At some point, there's a force between that basketball and the earth that are trying to, it's like a magnet. Have you ever seen two magnets smash together? You have a force between those. It's an attractive force, and there you go. All right, hell yeah. So what we can find this velocity because we know we have this component in the x. We know that this is the velocity component in the x. And we know we have to go a distance of 10 meters in 1.5 seconds. So the other thing to know is hell yeah, this is also an equation. You know what I mean? The only thing you need to worry about or know about these equations is this is acceleration average. This is velocity average. You know what I mean? I don't like to write it with the velocity average because I just want simple. I just want to be hell yeah, velocity, change in x, change in t. So well, what was my change in x? You know what I mean? Well, hell yeah, we went 10 meters. You know what I mean? 10 meters, and it took 1.5 seconds. Booyah, we already did that. I'm going to store that in my calculator as velocity. So we're just gonna store this as v. So this is the velocity in the x. So now what? What is that? Well, it just tells us that literally told us the velocity in the x. So now from our equation, we know that v of x is 6.7 meters per second, 6.6. You know what I mean? Repeating. And so if we go back to this equation, we got 6.6. Meters per second is velocity initial cosine of 40. And so, and then even right here, before you type in cosine 40, friggin' A, just draw a 40-degree angle. Say this is 100. That's a good way to do. If this is 100, how many is this? Does that look like 60? Does that look like more than 50? Hell yeah, like 65. Does this look like? Does that look like 55? You know what I mean? And I'm just using my best guesses. You know what I mean? To trying to get better at that. So now we're going to say, hey, what the hell is, and we're talking about now percents of the whole. So this is 1, and this is 0.5, 0.65. So if this is 40, we want to know what the hell cosine 40 is. So we go cosine 40. No, we were way off. It's 0.76. And couldn't we have done a check on reality? Because we already said that a 45-degree angle, we know this is 007.07. So if we actually get a shallower angle, well, doesn't this one get longer? Hell yeah. So this one has to be greater than 0.707. You know what I mean? And my guessing skills should have improved. And in any time that you get more than a 45, the classic is a 30-degree angle. Well, literally, this one is almost the same as this. Even though this is 0.866, 86.6%, you can very easily estimate it as the same. You know what I mean? Hell yeah. And at 30 degrees, this is the last point where you can be hey, is it still a small angle? You know what I mean? Because if you're calling it a small angle, you're basically saying, yeah, this is 1, not, you know what I mean? You're basically saying that these two are the same. All right, let's get some more light. All right, so what the hell do we know? We know that we wanted to find the cosine of 40. Cool. So we did it, and we got this as velocity initial times 0.766. So at this point, like we want to know the initial velocity. And another good opportunity to do a check on reality. We have a 40-degree angle. We already know what this is. We know that this is 6.6. You know, 6.6. And so if we know that this is a component, I mean, what's the initial velocity? Velocity initial is the hypotenuse, so it has to be a bigger number than the 6.6. And then so if we know, and if we know this is 40, so this is the faster way to do this. You know what I mean? I would write out the equations that, okay, I know the sun is shining on this side, so I know something about the cosine. So I would go cosine of the angle is equal to the adjacent over the hypotenuse. And then I want to know the hypotenuse. So I take the hypotenuse upstairs, and then I take cosine of the angle downstairs. So now I have the adjacent divided by cosine theta. So what I've been doing is like, hell yeah, we can do this faster. We can just see this is my angle. I know this is the cosine. And so what would I do to this number? I know that this number is the smaller number. What do I do to this number to get a bigger number? And the only thing I can do is either multiply or divide by the cosine of 40. And by definition, the cosine or sines has to be a number that's less than, from 0 to 1. Has to be a number usually less than 1. So if I take this number and multiply it by a number less than 1, do I get a bigger number? Hell no. So I just have to take this number and divide by cosine theta. That is mentally how I can quickly, do that calculation. So I have 6.66 as my component this direction. What the hell is my velocity initial? Well, it's going to be that alpha v, 6.6 divided by cosine 40. And now we're just money. And I'm going to store that as alpha w. And so we have the velocity initial. And again, this isn't answering the problem. This is just from the Seth Curry saying, hey, if it took 1.5 seconds to get there to there, well, and I'm shooting at a 40 degree angle, well, hell yeah. By that, I know from that approximation that my velocity initial is 8.7 meters per second. And now we can actually do this part that requires acceleration. You know what I mean? And it's still a guess, but now we can take it to Excel. And so what you would do in Excel is you would write out, because now what we're interested in, we're just interested in the height component. Because if you did this in Excel, you're like, cool, I know what my initial velocity is, so I know what my vertical velocity is. And I guess from here we need to actually know what Vy is, so we throw this value into Vy sine theta. You know what I mean? And could I figure out what the sine of 40 is? Well, sine of 30, that this component is 0.5, so sine of 40 must be bigger. I'm going to say, I don't know, probably that 0.55. So let's say sine 40. No, I'm way off again, 0.664. Well, and then duh, because, is 40 close to 45? Hell yeah, 007 on both of these. And so sine of 30, yeah, 0.5, so it's 40 degrees is closer to 45 than it is to 30. So yeah, I should have been guessing way higher, 0.65. Now, I hopefully won't make that mistake again. So I can sine 40, hell yeah, 0.65. I can just know that intuitively now. And so now we have that, and we already know this is our hypotenuse for our velocity initial. It is the bigger number. So now what do? We take that bigger number and multiply it by the, sine 40, 0.65. So we take alpha w, and then we have the sine 40, 0.65, and we just multiply those together. And we get a vertical velocity of 5.59, 5.6. Okay, I'm going to store that as alpha u. So now, how would we do this in Excel? Well, we need the first thing is 1, 2, 0.3, 0.4, all the way to 1.5. You know what I mean? Because At that point, hopefully it hit the basket. Now we need an x component. This is just our position. So we're saying, and we're going to use a datum of the floor because that's what they're using. X is, and I'm sorry. In this we'll have to do a y. We'll have, if it was just one directional, I'd be like, hell yeah, x is 0 here and x is the height. Height would be x. But we have two different things. This is the x direction positive. This is the y direction positive. So now I'm going to say this this is the y. This is the height. So the initial height of the basketball is 2 meters. So this is height in meters, and then we do the velocity. The velocity in the y direction. So the velocity in the y direction of that basketball. And I guess we need a times 0. So times 0, sorry about that, is 5.6. So now at this point, we need to know, you need to take the fact that this is acceleration, and you need to make it an equation, that it's change in velocity, change in time, is equal to the acceleration. And it is average. This is a good time to write average. But our acceleration due to gravity, it doesn't change. The other way to look at this equation when you have acceleration in the y is negative g. This is an equation. It is an equation with respect to time, because you could do this, t to the 0. Now insert any time at time 0 seconds. This is t to 0 to the 1. I mean, any time. So if we do 1 to the 0, well, hell yeah, that's just 1. And then our acceleration is negative g. Throw in at 2 seconds, you know what I mean? 2 to the 0. Well, that's 1. Our acceleration is negative g. Guess what? At y, this is also t0, y0. Because at our initial y of 2 meters to the 0, what's our acceleration? It's negative g. Cool. And so yeah, we just have the acceleration is change in velocity, change in time. So let's say, and this is an equation. We know acceleration. We know it's a number that's negative g. That's known. And in this case, we made up our own time interval. So our change in t right here is 0.1. Cool. And so we know that. So the only thing, so you can use this, that is the crazy thing about this. It took me years to be like, whoa, this is just an equation. Even though you have to say this is acceleration average, and if you have an equation for acceleration that isn't constant, what you're going to do is just take a smaller snippet, because the whole concept of calculus or calculus is just hell. Smaller snippet, guess what? That's just a level line. And so now we know our acceleration. Acceleration at that point is no difference than the average acceleration between just a small little cut. Okay, so and our cut is every 0.1 seconds. Alright, so now what we would do is just rearrange this equation. Change in t goes upstairs. Now we have an equation for change in velocity. That's going to be acceleration, change in time. So right here, we're going to write change in velocity. And in Excel, I don't mind doing it dv. I think this is a good point to do it dv because it helps you understand the basis of calculus, but also derivatives too. Because we're trying to find the change in velocity, and we had an equation that was a derivative. You know what I mean? We have an equation that says negative 9.8 is dv dt. You know what I mean? It's a derivative equation, straight up. Cool. All right, so from this equation, you throw in 0.1 seconds, you throw in 9.8, and guess what? You get a change in velocity of 0.98. So hell yeah. So that's going to be our change in velocity, 0.98. Then from that change in velocity, now you have to know a little bit something, because oh, my bad. The thing that I didn't do first. No, we did it. We said it had an initial velocity of 5.6, and if we did the units on this, this is a negative 9.8. All right, hell yeah. So the acceleration is a negative 9.8. So yes, we get a change in velocity of negative 9.8. So there you go. Our change in velocity is negative 9.8 over that 0 to 0.1 seconds. So now, right here, for our new velocity at 0.1 seconds is just this 5.6, you know what I mean, plus whatever this was. And it's a plus a negative 9.8. So this goes down. And then we have that. Now we need to figure out what the change in position is, because what we have is another equation that says velocity is change in x, change in t. But just like this was the acceleration that was average, or if we had a constant, it was like, sweet, we're just good to go. But here we don't have a constant. This has to be average velocity. You know what I mean? So we need another equation for velocity average. And what that says is, and I'll do this, 5.6 minus 0.98. So this next velocity is 4.62. So we have a velocity initial of 5.6. 0.1 seconds later, whoa, we reduced our velocity by now it's 4.6. Went from 5.6 to 4.6. You know what I mean? Whoa. So what was the average velocity? So if we started with 5.6 and now we're at 4.62, what's the average velocity? Well, it's just the midpoint between these two. You know what I mean? And you can do like high up math and just totally forget how to figure out what the hell is the midpoint between two numbers. Well, you just, you know what I mean, you add them and divide by 2, which is pretty cool. So even that, just to have that just dialed in your pocketbook. So there you go. That's velocity average. So let's do that. Plus 5.6 divided by 2. And we get a velocity average of 5.11. Now, why did we use that? Because we have this equation for velocity. You know what I mean? And we'll just say v is equal to change in t, change in x, change in t. What we want to know is how far it changed. And in our case, velocity is equal to change in y, change in t. So there you go. The average velocity in the y direction is what that's saying. So now we'll have we'll know how much we changed. This will be our change in y. And so we have we want to solve for change in y. You know what I mean? We have an equation. We have 3 things. We know change in t. We invented it, and so we can rearrange this equation. Change in y is bring the change in t upstairs. So velocity change in t, and this velocity has to be the average, but we did find that. And now we got 5.11 times 0.1. So now we have a change in height of 0.511. That's significant. You know what I mean? We're at 2 meters, and even after a tenth of a second, this basketball is 2.51, 11 meters up. Cool. And we just keep doing that. We keep doing that until, and this will run its course. Basically because we're always negativing the velocity. So we'll go, 5.6 minus 0.98 minus 0.98. And we'll just keep doing that until, whoa, now we have negative velocity. Yeah, no duh. Because now we'll have when we have negative velocity from this equation, then we'll have a negative change in x. You know what I mean? So we had our I totally apologize. We're in the y direction only right now, so velocity y, change in t. But when we have a negative change in velocity in the y direction, you know what I mean? Our equation for change in y is this: velocity times change in t. Velocity average will be negative. And then so we'll have a negative change in y. So now we'll be coming back down. And at the point where this Excel graph hits 2 meters, that's it. You know what I mean? That would have been the basket. And so what do we want to know at that point? We want to know what time that took. Because if that time wasn't 1.5, you know what I mean? Then our problem isn't right, because we just guessed. We went to YouTube, watched a basketball player take an actual basket, and we just assumed it's 10 meters. We did a pretty good job of knowing that, but those should be the same. Now, if they're not the same, then we have to adjust our initial velocity. You know what I mean? So we adjust our initial velocity till the time at the for that, for the Seth Curry shot, you know, if we're solving that problem, we know this is 1.5, you know what I mean? And we're hoping that this was 10 meters. So we just want to know, and we're hoping that he's 2 meters tall, and the basketball, that should be standard. But now the only thing that we'll have to tweak is this initial velocity in our Excel. We'll just have to keep tweaking it until 1.5 is where that basketball is at a height of 3.05 meters. Oh, bummer though, because that if we tweak that number, it's also gonna tweak this number. So no, actually, this is a one and done. This is a one and done. You can't tweak either one because we've already, from the video, have assessed that this distance got traveled in 1.5 seconds. And if that's the case, this velocity had to be, it is what it is. But the thing for the video that we could tweak is the angle. You know what I mean? Because this has to be rock solid 1.5 because that's what we did from there to there. But obviously, it's just kind of a guess. But that's from the perspective of why wouldn't my Excel match the video is because, well, maybe this angle is a little bit different. You know what I mean? Your shooting angle. But yeah, let's do it in Excel. I just don't like to talk into the computer. I'd rather do this because, I don't know, even though I kind of write small, the whole idea is talking through the concepts. It's not really, I don't mind if I write this tiny. But hell yeah. So let's go to the computer, type this in Excel, and see if it checks out. And then we'll come back and just solve the problem like normal. Right, hell yeah. So we're in Excel, and we do our time value first. So I'm just going to do lower t. And yeah, I don't know. Sometimes I just do we'll try to keep it simple. So we're going to go 0 and then 0.1. 0.1, and then drag 2, and we'll go all the way down to maybe like 2 seconds. And you know what I mean, you just want to do about this many cells because you might mess up, you might make a mistake and nothing makes sense at all, but once it does make sense, hell yeah, you can go 0.01, you know what I mean, and drag this hella down to 2 seconds. Alright, so then the next thing on my sheet, just so we stick with it, is the y value. And this is how I do it. This is in meters, t in seconds. And we're going to start and do some subscripts. This is y initial. Or no, I mean this is just y, whatever, At time 0, that's initial, you know what I mean? So there you go. So it's just y, and this is 2 meters. Hell yeah. Alright, the next cell that I have is my velocity. And this one I will. Velocity in the y direction in meters per second. And so we know, from what we calculated, that was 5.6. Let's just go back to... well, now, I think I made a mistake. Holy Toledo. Oh, no, I apologize. I was just like, well, I thought it took 10 meters to go 1.5 seconds. That was 6.6. Then we divided by the cosine of 40, and then we got the hypotenuse. But then we multiplied by sine of 40. And heck yeah, that's 5.59. So we're just right, 5.594, and that gets us real accurate. So yeah, I apologize. I was just like, wasn't our velocity 6.6? Well, yeah, that was the velocity in the y direction. So I'm sorry, the velocity this way in the x direction. We want to know the velocity in the y because that's what's going to be slowing down. All right, so then the next thing we do is change in velocity. Oh, and actually, I'm going to do this. I always do acceleration first because, hell, these are things I know. Time, I know my position, and I know my initial velocity. So now I go acceleration is meters per second, and then per second. See, even the units is the equation. It's velocity divided by the time component. Okay, so now what I want to know is, and then so we know this is negative 9.8. Cool. And then, so then from the equation, and I should have given myself some more room, but we know that acceleration is equal to dv dt. So I just write this in because now I can see that if I want dv right here, dv, change in velocity, so this is in meters per second, but it is the change. It is, and so if I rearrange this equation, I see that dv is equal to acceleration times dt. And then hell yeah. So this kind of spells it out. Now I can go acceleration times, what's the change in velocity? I just come in here and do this one minus that one. And all these, and they're good to go. So there you go. So that's that. This is my change in velocity. So even right now, I could go right here and say, well, I know that this is the initial velocity plus this is my change in velocity. And then now I have this velocity. Okay, but now getting back to it, we definitely need the average velocity because our next equation, the first two equations, you know what I mean? It's just write the equations first. Acceleration, dv dt, change in velocity, change in time, and then velocity is equal to change in position divided by change in time. And say it as change in position, change in time, even spell it out. I like to use the carets, but then use the D. I swear just writing a D just makes it, look like too complex of math or anything. But it's just an equation. That's the take-home point that I'm just oh, hell yeah. We have three variables. We have velocity, position, time. Cool. And it's not, it's well, it's change in time. Well, duh. We know what that means. You know what I mean? So now we're going to rearrange, and we want the change in position is equal to velocity times change in time. Cool. And so here is going to be our dx term. No, I apologize. We again, this velocity is velocity average. That's the only, you know what I mean, kind of, triple star that you need to definitely not forget. There you go. And then this acceleration, for sure, it's also average, but for these problems just involving gravity, it's just also a constant. You know what I mean? So hell yeah, we're good to go there. Okay, so now so now right here our next cell is just velocity average. In meters per second. And so, yeah, and this equation can be kind of stumping. It's what is it? Well, this is our velocity initial. This is our next velocity. So our the velocity average is adding them up and then dividing by 2. Okay, hell yeah. Now we're on a roll. Because now we just found the velocity average. And we want to throw it into this equation because we want to get dx, our change in position. And I apologize. I'm gonna call this dx every time, but for this problem, it's in the y direction. So apologize about that. So we have dy. So this is just our change in y, and it's in meters. And we have an equation for it. dy is this velocity average times our change in time, which is just these little time components. Okay, hell yeah. So now we know our change in position is negative 5.1, and everything, that's why I wanted to do it on paper first. So I'm hitting my targets. Whoa, this already feels pretty good. Okay, so now if I know this is my change in, and this is a positive, the thing is going up in the positive y direction. I gotta pinch myself. We are going in the y direction. And then so I know that at this at time 0.1, I know that we have to go from our initial y plus our change in y. That was the whole reason for that. Cool. And now just on repeat. Now I have a new change in y. I have a new velocity in the y direction. Acceleration, we can just pull this all the way down. Or we'll just pull it down once. We'll pull everything down just in a second. And then, so now if this is my acceleration, well, I need to know my change in velocity. And guess what? These two columns are just going to be the same the entire way down, because change in velocity is the definition of acceleration, and it's constant. Some problems this won't be a constant, and that's why you use Excel. So that's why I'm just going over this one, because it's really useful. Okay, so now if that was my change in velocity, well, hell yeah. Then I'm just going to bring this down, and what was this? Well, this was this initial velocity plus my change in velocity. Cool. Now that I did that, I can bring this velocity average down. What the hell was this? This was just adding those two up. Now we're trying to find the velocity average between those. If we do, hell yeah, we can bring this cell down, because that says that we take that velocity average and then multiply it by the change in time. And this just shows you why position is a second derivative. I don't say it ever like that of time, because I don't know, I probably should just get used to the technical jargon, but all I know is, like, hell yeah, it's a function of time squared. And no, let's write this will be really helpful for me. Acceleration, it is dv dt. Cool. But guess what? But v is also dx, you know what I mean, dt. So if we actually put those together, we have acceleration is d and then dx dt, and then divided by dt. You know what I mean? So it's not a pretty way to do it in Excel, but essentially what you'll get is d. It's this d squared. It's the second derivative, d to the 2 of x divided by parentheses dt squared. You know what I mean? So don't think it's the dx squared up top. But anyway, I'll have to learn more about that. But definitely, take home point, all I'm just getting at is, hell yeah, the downstairs component is just the change in time squared. And so we just see that. We see that the change in time squared comes out here. Hell yeah. And then again here. Okay. So now let's rip these down. Rip it and grip it. And we'll see if our problem even came out how we wanted it. We're trying to shoot for this 1.5 mark. And we want, what do we want? We want our height to be 3.05. That was the problem. It's not, but let's pull it down one more. No, it's hella not. So, whoa. No. We messed up something, because we're going up. We shouldn't be going up. So, yeah. Because the change in y is right, but now we go here, and then that. So this plus that. Oh, but why didn't... Oh, whoa. I apologize. Holy Toledo. So this acceleration, sometimes it does that, where it pulls it down and it wants to change it. What did it change it to? Yeah, it just wanted to add -1 the entire way. That was a nightmare. Okay, hell yeah. So now do we get the right answer? No, we don't. So the ball goes up, and its top height... See, even from this it started at 2, and with that initial velocity, that's bizarre. Yeah, that's nowhere near. So I'm just gonna take a pause, just because at 1.5 seconds, yeah, it hit the floor. You know what I mean? So a couple things is that Seth Curry's shot probably wasn't 10 meters away. 10 meters is a hell of a distance. I mean, if the 3 is at 1 point, if the 3-point line is only about 7.5 meters, let's say, then it's another 8 feet past, and I just don't. Yeah, so we'll just crank this up to like 7 meters per second, and getting closer. So we'll keep cranking it up. 8. And where do we get? Well, we got to crank it up a little more. 8, 9. And so if we crank it up to 9, we get, that's too much. So we'll go 8. And then at this, well, we're shooting for this 3.05. You know, we saw a shot, you know, in 1.5 seconds, hit the so 3.05, so we got to go a little bit more. 8.1, and yeah, that was too much. 8.05. Okay, so there you go, 3.05. So let's start with that, and at least we got an answer. But that's the cool thing about Excel is once you have this, like we did everything right. It just shows that you know what I mean. Our assessment for where Seth Curry was probably bad, and so even from here, what we can do is back calculate. What we saw is Seth Curry shoot, hopefully at a 40-degree angle, and it took 1.5 seconds to get to the basket. If he's at 2 meters, the basket's at 3.5. We need this trajectory, and to do that, it would require, like it doesn't matter. This 10 meters is irrelevant. Irrelevant. You get what I'm saying? Irrelevant. It's irrelevant to our problem. You know what I mean? Because we're just saying if Seth Curry shoots a basket at 40 degrees with this velocity, it's going to exit his hands at 2 meters, and at 1.5 seconds, it's going to touch an object at 3.05 meters above the ground, and that was the basket. This is the basket that we saw Seth Curry take in the video. So now from this, our velocity was much higher. So this is interesting. I don't think the shot was taken at a 45-degree angle. So maybe I'll input that clip right here. Probably not. I don't want to waste too much time on this. But so now what we can do is say, hey, this was our velocity in the y direction. So I'm just going to I'm going to print this, and we're going to take it back to no. Yeah, I think we need to take it back to the paper. So we're done with here, and let's go back to the paper. Alright, so we're back, and we got the Excel sheet, and we're going to say this velocity is 8.05. Let me get this in here. And so this was the velocity in the y direction. And if our angle is 40, you know, we're saying this is velocity y. So now we want to know the velocity in the x direction. And because I just want to see how many meters the shot was from this example, just to make sure I'm not just way off. And so if I know this, and I want to get this, well, I mean we could get the velocity initial. Might as well do that. So what do we do to this number to get that bigger number? Well, we're gonna take 8.05 divided by. This is the sine component, so sine of 40. You know what I mean? I already know that angles, the angle the sun is shining on the sine. I know the sine component. I want to make it the hypotenuse, the bigger number. So I'm going to go this number, 8.05 divided by sine of 40. Because dividing by sine 40 is dividing by a smaller number. A normal number divided by a smaller number, hell yeah, we get that hella. And so we have initial velocity of 12.5 times 2.25, 28 miles per hour. You know what I mean? That sounds reasonable, especially, you know, with ball sports. You know, with baseballs going 100 miles an hour. But a basketball, it's a big object. Okay, so let's see if this is going to make sense. So now this is going to be our new velocity. I'm going to call it R, I guess. So we're going to say this is stored as R. And we want that x, so we're going to take r cosine 40. You know what I mean? That's the one that, you know, just in engineering or just This one you got to pop out all the time. We already know our vector, you know, or our hypotenuse or a bigger number. We want to know the component of it. And so it's always just that bigger number times that fraction, you know what I mean? And that fraction is, you know what I mean, cosine 40 in this direction. It is sine 40 in this vertical direction. So sun is shining on the sinus. This is the cosine, our cosine. So we got this 12.5 times cosine of 40. And so we get a velocity in this direction of 9.59. I'm going to store that as alpha q. And so we have 9.59 meters per second. And then we had a time Seth Curry shot in 1.5 seconds. And then even this, just something super simple. How do you be like, ah, damn, I don't know the factor label method. There's so many times where you're just like, okay, I have this number, and what do I multiply or divide? Well, this number, the units, you know, I mean, kind of spell it out. I have meters per second, and this one I have second. What the hell do I want? I want meters. Cool, it's already on the upstairs, and then I can just, the seconds will cancel. So 9.59 times 1.5, and we're 14.39 meters. So I'm going to take a pause just because, like, you know, I mean, the physics shouldn't lie that he took a shot and it took 1.5 seconds and it traveled that far. But the trajectory, you know, we could give the benefit of the doubt that the trajectory was a 45-degree angle, and that's going to get that's going to make this, because this was like a shallow angle, and that's the thing. I think the angle is what's causing this problem. I don't think he was 14.38 meters away. But just in Excel, this one is hard because it's really hard to change that initial velocity based on angle. But what we do know, I guess we do know, if we assume then that, hell yeah, he was no more than 10 meters away, you know what I mean? Because this is not a check on reality. I do not think he's you know, because, you know, divide by 2, well, the 3-point line is only 7 meters away, and we're saying this is 14. So now what we're going to do is find a way to input the angle in Excel. So, you know, even just thinking through that, like, how would I do that? So I know that the velocity in the x direction now, based on that video of 1.5, has to be a velocity of 6.66 meters, because we have 10 meters in 1.5, 10 meters per second. No, time. Oh, did I do that wrong? Holy hell. That's so embarrassing. No, I apologize. You know, that's why we do these. You know, we have a glaring mistake right from the get-go. And I don't mind that. But this is like, see how I'm just trying to, like, explain my way out of this error? You know what I mean? Just like, well, he's not 14.38 meters away. You know what I mean? Maybe the angle's different. But holy Toledo. I mean, just thinking about that statement is like, well, what the hell is the difference between a 5-degree angle and 40? We're already at a pretty ideal angle. So this whole video came down to, and exactly what I just did right there. I mean, this is literal gold, because you will do this as a student. You'll be like, okay, I once I actually know the concepts, and then it's a sign change, and this is the literal worst. So we have meters per second, the two values that we're given is meters. Okay, we know 10 meters, and I know seconds. Seth Curry, 1.5 seconds, and then the meters was 10. So we want a units of something that's meters per second. No, damn it. No, we didn't make an error there. I wish I did. Yeah, this 10 meters per second, that was an error. My apologies. No, we're still back where this doesn't make sense. You know, not too much, you know what I mean? Like, I want to really assess how far a 3-point line is, recheck that value on YouTube, on Google, and then really assess, You know, even get down to measuring it out. You know, even from video, like you really know accurately what this distance is, and just by vectors you could figure out where he is. You know what I mean? Just to make sure. But hell yeah, we want velocity in this x direction. That is 10 meters, 1.5 seconds. So yeah. So that didn't change. 10 divided by 1.5. Okay, so we're still back that this has to be our velocity in the x, and what we want to do is make an Excel where we can vary that angle. And so you know, again, we have velocity initial is, and this is velocity in the x of 6.66. We know that. So so now we can just relate an equation with angle and this velocity in the y. This is the cool thing about knowing trigonometry. You don't have to find the initial velocity and then find y. You can, you know, the three things you should know with angles are the ones that I've just been spouting. Is like, hell yeah, this is the sine component, this is the cosine component, and this is your angle, and then all that stuff we talked about. But the other one, the other most important is like, hell yeah, if your components, not the big number, not the hypotenuse, but the other components, we need to know that tangent of that angle is the sine component divided by the cosine component. And you know what I mean? And it can be sine of the angle, it can be cosine of the angle, it can be this actual length. And again, this actual length was big hella sine angle, and this length was that hella cosine theta. But if you did that, the hellas just cancel, you know what I mean? So at the end of the day, you just have a ratio between the fractions, you know what I mean? And this is by definition tangent. And this is also, so we you know, and in your calculator you can just put tangent and 40 and get that ratio between them. And so let's go back to this one, because if we say tangent of the angle is, it also is the velocity in the y and velocity in the x. So if this is the velocity in the x and that's the velocity in the y, tangent of the angle is the velocity in the y divided by the velocity in the x. You know what I mean? Cool. Because those are just proportional to a distance component. Alright, so yeah, hell yeah. So you do have that little relationship. And just back at it, just how to do that simply is, hell yeah, I got this. I know tangent is that divided by that. Like, real simple. Tangent, you just, like, the things that you should be thinking is tangent. Well, that's sines on top, cosines on bottom. So hell yeah, if this is your angle, tangent of this angle is equal to, hell yeah, that divided by that. Because sun is shining on the sine in first, so tangent of this angle is that divided by that. So, you know what I mean? Hell yeah. And so we get this ratio, and then so we can just know that Vy is the velocity tangent of the angle. So now we can have a column. We can just have a variable up here that's angle, and we just want to vary it. You know what I mean? Because we want to throw in a 45, and that's going to output this Vy. So when we do Vx we know is that stored in our calculator as V. So we go V, alpha V, tangent of 45, and then we get a velocity of 6.6. Because in our problem, you know, we printed out the one that actually worked, but we started with 5.6, 5.59 or something, 5.59. But now with the velocity, with the angle of 45, that goes up. Tangent of 50, hell yeah, it goes up more. Because that's what we're seeing. And I went back to the video, and it's just like, hell yeah, that ball was sky high. You know what I mean? So that was interesting, because the time doesn't change too much. But because of gravity, this thing is hella wanting to magnetically, you know, attract itself to the earth, like, just, you know, it's like very, you know, very, you know, gravity's friggin' powerful. So hell yeah. So just even changing the angle to 50, So this is a real world problem, you know, and we took it from the perspective that, hell yeah, the YouTube doesn't lie. Seth Curry took that shot in 1.5 seconds. I am going to do a better analysis on figuring how far that was away to get to maybe dial in, because the other component is this v of x. You know, we've already said that it's 6.66 or 10 divided by 1.5. And then so for this initial Vy right here, for this value, we're going to, booyah, Vy is Vy is Vx tangent of the angle. So here's our input, and then here is our input. And this 10 I might change. You know what I mean? I can also say distance. I can also say x is 10 meters. So then this value will reference that cell, and so now we can start playing around. But I did the time frames, and it was 90 frames. It wasn't 95. It wasn't, you know. So I'm within 5 frames of being at 1.5 seconds. So it's a very reasonable time. If it was less, but if it was less, 10 divided by 1.5. If it was 10 divided by 1.4, yeah, this number, I'll check it again. You know, I'll do that too. Because do you do the release? Because if you do where the ball releases to where it like just barely touches the rim, yes, I bet you I can make up for a few frames. So we're going to make those, and I'm going to reassess that distance. I'm going to reassess the distance, and I'm going to check all the frames and make our change in time more like 1.4 something. And that's going to increase that velocity. Okay, so hell yeah. So we're going to go back to Excel, and then hopefully dial this problem in. All right, hell yeah. So we're back in Excel, and you know, we want that theta, that angle, and in degrees. And so we're going to put that right here, and we're going to do 45. I guess we could do 40 and see if it comes out again. And then then our equation for this Vy right here, well, we got a couple more. So we do have our x, and we're going to say the x was 10.58. 10.58. We're going to store, and that's x in meters. We're going to do time in seconds. And so this is going to be more accurate. It's going to be it's going to be 1.5 times equal 1.5 times the ratio of 85 divided by 90. Cool. Whoa. Yeah, so 1.46. Okay, so now we'll know our Vx, and so we're also gonna do Vx right here, velocity x meters per second, and that's going to equal this distance divided by seconds. Cool. So we get velocity of 7.48. So now we can know that our initial velocity upward, Vy, is that equation. I mean, can we rattle it off without looking in our papers? Because we were going to say if we knew Vx and Vy, so it's a relationship with the tangent of 40 is Vy divided by Vx. So it's Vx times tangent 40. So it's going to be this Vx. And then we got to do function F4, $2 on that. So when we drag this down, that value stays the same. We take a look at that. But times tangent. Now the angle has to be in radians. So we can take this angle of 40, but then we got to divide it by 360. That's the first thing I do. You know what I mean? Hell yeah. You know, because now we're you know, a portion of a circle. We're 40 3/60ths of a circle. So now we just have this ratio, and then we get to multiply by 2 multiplied by pi, and then yeah, and then we're just good to go. So now that, and we can do a double check in our calculator. We have 7.4 times tangent of 40, and that's 6.2. Cool. All right, sweet. And and hopefully that made sense. But yeah, because with an angle of 40, this is a bigger term, and then this term is a little bit smaller. Okay, so now that we have that, how did that change our problem? Oh, you know what I mean? And so our problem, we'll drag it down now. We got to drag that value. Whoa, whoa, whoa. What happened to this? Oh, yeah, because this one also, sorry, this value is also have to go function F4, $2 signs on that. Whoa, whoa, whoa. And $2 signs and then enter. Cool, we can drag this down. Okay, heck yeah. Oh, you know what? We only get to do that once. And so not, shoot. So let's figure this out. So our acceleration is this. Our change in velocity is that. So this is going to be this plus that. And now we can drag this down. Cool. So now we have a velocity in the y direction decreasing, hitting a 0, and then at time point 6, so at 1.7, it should be back to that same velocity. Okay, so that's all checked out. But now our at 1.5 seconds isn't the parameter that we're looking for. It's so I'm gonna, because that was part. It's like 1.4. Basically at 1.41, this is where this is the time that this basketball should be 3.05 meters. So I'm just going to make this yellow. Cool, and now we can adjust, we can turn this to 45. Hell yeah, that went up. See, it's 2.85. Let's go 50. You know what I mean? That's not out of the question. And now obviously we're way over 50-degree angle. With that velocity, we overshot. Okay, so now we're gonna go 47 less. So now we got to go 46, 45.5. Whoops, 44. Oh shoot! What the hell happened? Oh, I don't know what I was doing. So 45, 45.5. There you go. 45.6. Too much. So you got 45.55. Hell yeah! And then we get so that's going to hit that rim at 3.05 meters. So there you go. So the only thing that we for sure knew was the time. The distance we were kind of sketched. So I'm just going to write this down. So we have 45.5 degree angle. And the other parameter that we can change is this. We thought at a minimum this was 9.06. So now we're going to go back to that 40-degree angle. And now we're hella off. You know what I mean? So let's go up to 50. And oh, we're pretty much right in there. So 49.5, 49.9. Whoops, 49.9 and 49.95. Hell yeah! So we're right in there. So this angle would be 49.95, and there you go. Like we have what I think we've learned from this is no one's taken a 40-degree shot from 10 meters out. You know what I mean? I think we've debunked this problem that doesn't happen. I would like to set this up for all NBA threes and maybe get some footage because they do stats on this. You know what I mean? I think they can, with all the computer technology, they can know exactly how far out that basketball player is. Hopefully that's a stat they take. And then we can definitely from YouTube figure out the time, and then you can do an average of like, well, if you are doing long threes at 10 meters out, like what angle are you shooting? Are some shooters shooting at a lower 40-degree angle? You know what I mean? Is this problem dumb from that perspective? Because it looks like from our conclusion, if you're closer and you shot it in that time, you had to. Does that even make sense? that if you are if you're closer to the basket at 9.9 meters, and that means that what does that mean? That means you're going to be slower shooting. You know what I mean? This velocity is slower. Yeah, so you need more hang time. That is interesting. But the farther you get, hell yeah, you got to shoot directly at the basket. So, like again, if you were shooting directly at the basket in a line, and you were going for 1.41 seconds, um, well, I mean, yeah. Well, let's do that. Well, let's just pick a. I'm just curious because we can change this angle to like 5 degrees. Let's just do 10 because 5 might be a little bit crazy. And for this 1.4 seconds, like if we wanted to, I don't know if that would make any sense. Um, no, that's going to be a different problem. So anyway, well, let's go back to the paper. I think let's undo that. I think I think I learned what I wanted to learn from this problem. That closer to the basket, you got to shoot higher for that Seth Curry shot because we timed it 1.4 seconds. So the only way for him to be closer and make that same shot is if it was higher arc. And you see it's a pretty high arc shot. So that's the only thing that we don't know is how far he was away. If we could really dial in, whether it's between 9 and 10.58 or whatever I said, if we got that dialed in, we would know exactly the angle of the shot. All right, let's go back on paper and solve this problem as it is. All right, hell yeah. So I think we can increase the meters to 10 to 10.58 meters because, all right, so this was cool. We got the full dimensions of a basketball court, and this, between this, half circle or whatever, that midpoint is the center of the hoop. So there you go, center of the hoop, and we're 7.24 meters to the 3-point line. And I'm going to say this. I measured with my ruler from there to there. We got 93 millimeters. And then to here we got 136 millimeters. And just by the way the camera is, I definitely know that this distance, or is this going to work out? Bummer. So I think it's the opposite. Well, I know that this distance is 7.24 meters. I'm so bad at ratios. You know what I mean? I'm just assuming that. So what I did is I said 7.24 divided by 93 millimeters. So this is going to be this many 0.077 meters per millimeter, and then we have a total of 136 times 136. Now, for the life of me, let's say the perspective was so bad that, like, hey, the hoop was right there, the 3-point line was right there, and then this person's like standing right here, and then so I'm definitely overestimating. So that's a bummer. So I'm hopefully the perspective ain't too bad, but just from that, it's good to do these things. Like, am I underestimating or am I overestimating? And from that scenario, I'm definitely overestimating, but let's run with it. And then the other thing is I found that it was 85 frames. You know what I mean? Because I was thinking it was 90 frames. 90 frames is 1.5 seconds. So how the hell do I do this? I go 1.5 divided by 90 times 85. So I got a lot of different ways, but I'm not going to worry about that. So anyway, so the time is 1.16 repeated seconds. And so there you go. And now we're going to take it to Excel and play with the angles. But we are going to use this. So now that I know what the hell is my VX, I'm just going to do it. But this might be a little high. Like, obviously this might be high. Like, we were from this, we can probably just go back to our original 10 meters, call it good, and hopefully that's fairly close. But so if we have 10.58 meters in 1.4 seconds, I got to store this as alpha t. So 10.58 divided by alpha t And so we have our new stored as v. So we have a velocity in the x of 7.468, and now we're on our way. The only element of this is this perspective. I know that this is a little bit shorter. I just don't know what the perspective is with the camera. You know what I mean? What do you do? What do you do? I guess there could be ways to figure that out, but I don't know. I mean, I could figure out what the distance to there is compared to the distance to there, because look at that, look at this, that shows you, and then the distance to there, so you can kind of see like all of those lines should be the same length, and they're definitely not. That's a three-pointer, that's a three-pointer, that's a three-pointer. So yeah, it's tricky, but yep. I just don't know. I mean, if I looked at this, I would say, you know, maybe right there, and hopefully that's underestimating. But still, I still can't do a ratio on this because the perspective is real small, and then it gets bigger perspective over here. So like, how else would I do it? You know what I mean? The other way is like, well, do I think this distance is farther than this distance? You know, for sure. Do I think this distance is about the same as that? I think this distance is a little bit shorter. So I could just say it's a 3 plus that. And this distance is 12, so half of it's 6. So I'm gonna say it's a 3-pointer. So we got 7.24 meters plus 6 feet, and we go 12, 25.4, and then divide by 1,000 to get that. So 6 times 12 times 25.4 divided by 1,000, and this was 12 inches in 1 foot. This was 25.4 millimeters in 1 inch. Inches cancel, feet cancel, and this was 1,000 millimeters per 1 meter, and so we get an extra 1.828. I'm going to store that as x plus 7.24, and we get 9.06. So there you go. So on the low end, we're going to be 9.06 meters, and divided by 1.4 divided by alpha t, and I'm going to store that as alpha w. So we're going to be in between 7.48 and 6.4 meters per second. But yeah, somewhere in between there is the actual velocity. I think this was an undershot, and then, you know what I mean, this distance, yeah, it looks like this distance is definitely farther than that distance. It looks like this distance is, he's definitely farther than that distance, that's for sure. Okay, so I think we got our numbers. Let's take it to Excel and see what we get. Alright, hell yeah, now we're back. And guess what? We're just going to solve it like we would just any sort of, you know, normal problem. You know what I mean? We want a couple equations, you know what I mean, a couple unknowns, and then solve for the one that we want. And in this case, we have two different, you know, you're looking for two different relationships. You know, so there's one relationship that says, hey, the velocity times this time has to equal that distance. And the other one says, well, you know, the velocity up is related to the acceleration, and then at some point, you know what I mean, the ball is going to go up and then it's going to hit there. So the time it does to take that has to equal the same time it takes, you know, for the ball just to go with the velocity this way times this distance, you know what I mean? So if I knew the velocity, meters per second, and this distance, so if I did know that, meters per second, and this distance meters, how would I get seconds? You know what I mean? There you go. You know, seconds has to be on top, so we would take meters, and then we would divide by meters per second. Pop meters upstairs. So we would need distance, so you'd do 10 divided by whatever that Vx would be. And so that's what we were doing the whole time, 10 divided by like 1.4, and we get that initial velocity. So anyway, so hell yeah. So without further ado, but we are going to take kind of one tangent, is because I'm going to use the integration approach. And then for whatever reason, the second we do the magic trick of integration, like my mind shuts off and I do not see this. You know what I mean? Like I have never visualized that the second I do the magic trick of integration. You know what I mean? Only that's why we set this up in Excel to be like, well, hell yeah. We kind of took a DT, a snapshot in time, and then tried to figure out what the so we're gonna at least slow down through that part, but here we go. So we're gonna have some sort of initial velocity, Vx initial, and then Vy initial, and that's going to be my vector there, just V initial. I'm gonna say that so we have meters per second times or what did I say? I said you know, I guess there's a couple ways to frame this, but I mean you could do 10 divided by t is equal to, well, that must have to equal Vxi, you know, velocity in the x direction. Because we have meters divided by seconds, you know what I mean? But there's three ways to do this. You could also say that you bring the t upstairs, Vx of t is equal to 10, you know what I mean? And so that's probably what we'll do. Or you could say, like, what's the other? Like, we have three variables here. There's three ways to arrange this equation. Sometimes it's fun just to do that. I don't have one that has t alone, so we're going to bring the t upstairs. Time is 10 divided by Vx initial. So there you go. But we'll use this one. So that's one continuity. We say, hey, velocity initial times time is equal to 10 meters. Cool. We have our first equation. Now the second equation has to do with this velocity, the vertical part of the velocity. It's going to be hella change in velocity, change in time because of acceleration, and that's negative 9.8. And so what I do integration style is say that acceleration is negative 9.8. And then I definitely write the equations. Acceleration is change in velocity, change in time. Velocity is change in position, change in time. Anytime you're doing this, these are great equations to write. And so we can see that also acceleration is dv dt and velocity is dx dt. So right here, I can substitute dv dt for acceleration, you know what I mean? And hell yeah, now you're doing actual physics, you know what I mean? This is how your physics problems should look. They should look like differentials. Because once we get a kind of, do you call this a differential? Yeah, I don't know, but we're definitely going to separate variables. Now for this, like I said, this could be t to the 0. This could be x to the 0. It could be anything to the 0 you want it. But basically, things that we know are time, position. It could be velocity to the 0. You know what I mean? Acceleration is a function of velocity to the 0. Right, it's not a function of velocity. You know, that's basically what that's saying. But when we separate variables, you know what I mean? Because we'll have this, negative 9.8 t to the 0. Well, hell yeah. Now we can bring this dt up here and then have the dv. And we can just know that anytime we have like a dt, do we just with like a constant of negative 9.8, you know what I mean? It's just alarm bells should go off that, well, if this is a constant, obviously, like that's, it's you know, it's not a function of time, you know what I mean? It's not, but then when you integrate, hell yeah, this dt is a function of time. You know what I mean? Oh, and that's fascinating to me, because if I do take these little chunks of dt from like 0 to whatever, you know, 0 to time is equal to whatever, 0 to t, heck yeah. Oh, so I get it. Yeah, if you're integrating from 0 to t, hell yeah, this dt goes to t. Because if we do this, you know what I mean? If we just integrate 0 to t dt, oh, see, so now I'm kind of learning why all the intermediate things, like, you know what I mean? So this is t to the 0 dt, and then we go, the integration of that is t to the 0 plus 1 divided by 0 plus 1, cool, plus a constant. So we have t to the 1, you know what I mean, plus a constant. And then and then we evaluate it, and I don't know what this actually gives, but anyway, yeah, I'm just trying to walk through all the steps, you know, like the nitty-gritty steps, so I'm just not missing something, But here we go. We're going to separate variables. Now we're going to get dv is negative 9.8 t to the 0 dt. Now we can integrate both sides, and we get, hey, this is v to the 0. That's, if you just have dv, I bet you could put v to the 0, because now we'll get integration will be, I don't think so. Don't do that at all. But anyway, dv, just like this, the integral of it just goes to, yeah, so this is just v, and this is going to be an equation for vy. In the equation for v, the vertical velocity as a function of time is now going to be negative 9.8 t to the 1, or 0 plus 1 divided by 0 plus 1, plus a constant. So we're going to have vy of t is equal to negative 9.8 t to the 1 plus a constant. So now how do we figure out this constant integration? Well, we're going to say at time 0, you throw a 0 in there, what do we know about our velocity at time 0? Well, that's going to be vy initial is equal to negative 9.8 times 0 plus a constant. This is 0. Our c is velocity vy. So our equation, go back to this, vy of t is equal to negative 9.8 t plus vy initial. And now we're good. Now we have an equation for velocity. What we want is an equation. What do we want? I think we just want to integrate one more time. And but again, why did we even integrate negative 9.8? We said we have acceleration is plotted on a line at, well, I guess it's negative. So we have negative 9.8 as a function of time. Remember how we were saying this is t to the 0? As a function of time. So at every time interval, we have negative 9.8 as our acceleration. So we go back to the definition of acceleration as change in velocity, change in time, because we would want to know the velocity. So the area under these curves, if this is 1 second, the area of this curve is, so now we'll do the velocity graph on top of here. So now, if this is acceleration, we can do the velocity graph, and we'll have, at 1 second, we'll go up, let's say that's just 9.8. I guess it's in the wrong direction, because this is a negative, obviously, so yeah, let's do it. So now our velocity, so if our velocity was 0 and now we're going a negative, so at 1 second we're going to be at negative 9.8. And hell yeah, this is exactly why I should slow down. That's why I was just hand waving it. No, let's do it like legit. Here's your acceleration graph, and what the hell does this mean? Well, take a square and then figure out the area. And then what the hell does that mean? Well, let's get some units on this. This is meters per second. And guess what this is? This is 1 second, 2, 3, 4, 5. So now you're multiplying by the 1 second, and now you have 1 second times negative 9.8 meters per second. So let's do that over here. Negative 9.8, and this is why you should write acceleration as meters per second, little brackets, and then divided by seconds. Because now when you multiply by 1 second, seconds easily visually cancels, and you're left with negative 9.8. And this is a velocity graph. This is acceleration. So now at 2 seconds, well, guess what? You'd find the area of that square, and you're going to get another. The area of this is negative 9.8. And let's see. Because this distance is negative 9.8 meters per second, and then this distance is 1 second. So those cancel, and again, now we have another negative 9.8, but it's already in addition. The thing about, so, Yeah. So this is where I always got confused. It's like, hell no. Once you find the area, you are no longer finding the area of squares. You are finding points on a graph. So if I'm integrating and adding up areas, I'm getting points. You know what I mean? So, and then the areas are additive. So we have negative 9.8, negative 9.8 plus negative 9.8 minus 9.8. And so we get negative 19.6. Do the next one, and we get negative 29.4. So now we have, and we're already at 3 seconds, which is plenty for what we're doing. So now we have a line like this, and now we want to find position. So even from this graph, let's think about it. So now our position is going to be at 0, because we need to talk about that constant of integration. Because let's say we do have a position of 0, you know what I mean? So if we call that 0, well, the ball is just going to fall to the floor. So if we have a position of 0, then we're going to add up that triangle. Now this triangle is negative 9.8 meters per second times, and check it out, 1 second, 2 second, 3 second, times 1 second. And then seconds cancel, but guess what? This is half. See how the triangle, area of a triangle is half. And so that's where this comes. So if you have a constant, you integrate it. That's why you just get velocity is negative 9.8 t. But then you integrate it again, then you get negative 4.9 t squared. And we're going to see how that is position. And we're going to see how that adds up. Because the second you add up this tiny triangle, well, guess what? The next one, you're going to add up another tiny triangle plus a big square, a big rectangle. Then you're going to add up another tiny triangle plus 2 big squares. You know what I mean? So so every time you're going to add one more big square and then another small triangle. And you know, even visually, I don't know why that's x squared, but I guess it is. I guess it's because x squared is kind of an exponential. But yeah, because well, even if you just doubled the area, even if you had something that was just like, hey, if I have 2, and then next time I have 4, and then next time I have 8, well, that crap's going to blow up. Now this is way more blow up-ish. This is 2 to the x. Now 2 to the x is way more blow up-ish than x squared. But this isn't doubling it. You know, we're going 1 square. We're just adding another. We're just adding another square. But it is that x squared graph. So let's take a look at why that is. So here we have our first is going to be a negative position of negative 4.9, negative 4.9. And then so once we get that, our next position is another negative 4.9. But then what the hell is this? This is negative 9.8. Because the dimensions on this thing is negative 9.8 meters per second times 1 second. So now we have negative 9.8 plus negative 4.7. So negative 4.7 minus 9.8. And you get negative 14.5. So even just right there at second 2, you're already down there. And then this isn't to scale now. So I have negative, 5, 10, 15. So we're already like right there. So you see how the x squared. Let's go one more second. And now what the hell are we going to add up? Well, we're going to add up, we have negative 19.6 meters per second times 1 second. And then plus, you know what I mean, plus a negative 4.9. So negative 19.6. Minus 4.9. So hell yeah. So now we're 5, 10, 15, 20, negative 25. So now we're down here at second 3. So we went from and is that right? Is that right? Because if here's our equation at second 3, negative 4.9 times 3 squared. Yeah, it's negative 24.3, and that's kind of what we got. Oh, whoa. What the hell did I just do? Because I think I do have an error here. Times 3 squared. Yeah, no, I thought I had an error here. It's just like, so right here, so negative 9.8 minus 9.8. Okay, so here's those. And Okay. Oh, we're adding the areas. So I took this and then I just added it to that. I even forgot what I was doing. No, you have to sum up all the areas from the get-go. So that area is negative 4.9. This is negative 4.9. That's negative 4.9. This one is negative 19.6. And then this one is negative 9.8. So if we added all those up, negative 19.6 minus 9.8 minus 4.9 times 3. Yeah, we get negative 41. And isn't that what our equation says? Our equation for x, once we integrate it, will be negative 4.9 times 3 squared. Yep, perfect. So so we are going to get an exponential. And now 5, 10, 15, 20, 5, 10, 15. So this is already an x squared graph. Okay, hell yeah. So just that, adding the I'm going to do that more. Even though it just seems like, why the hell would you do that? Because the second I go to integrate stuff, it's a magic trick to me. It's hand waving, and I'm not focused on any of these adding triangles. And I've made a mistake this week of being like, hey, when I add the triangles here, it feels like, well, you get something else. Yes, you get something else that you could add those triangles to. But the second you sum these triangles, you are getting an equation for those areas. You know what I mean? End of story. You don't get two things. I even made a graph and I was just like, oh, look at that triangle. Look at that. Well, sure. Later on you can do that, for the next integral. But if I'm just summing the area, I'm just getting these points. These points represent the area from there back. All right. And that's why if you get any point, if you have a constant, it's just like, hell yeah, I got 8 seconds. Well, 8 times negative 9.8, and we can do that. Negative 9.8 meters per second times 8 seconds. Super simple. You know what I mean? It's just whatever the time is multiplied by whatever the constant is. But this next one, also super simple. Like whatever the time is, if my time is 3 seconds, multiplied by well, you got to get an equation for this. Whoa. No. It's as simple as this. It's whatever my time is. So I would go negative 9.8 meters per second times 3 seconds. Now, per second. Now, why wouldn't this be velocity? You know what I mean? Well, it's this isn't velocity, because taking an acceleration and multiplying by time is the definition of change in velocity. Let's go back to our equation. Acceleration is change in velocity, change in time. Therefore, if we take acceleration and multiply by time, we're doing change in velocity, change in time, multiplied by time. And if we do this, you know what I mean? We're basically change in time, we're getting change in velocity. But what we're not getting is the velocity at. We're not getting the velocity at t is equal to 3 seconds. We're getting the change in velocity from 0 to 3 seconds. Now, I should be, you know what I mean? For me, isn't that the velocity at 3 seconds? Because if we got negative 9.8 times 3, that's negative 24.9. That is the velocity. So yes, that is the velocity. Because acceleration is a constant, this equation holds. It's a legit equation that acceleration and its average, but it's totally equal to the change in velocity, change in time. I can pick any two changes in times, and then multiply that by acceleration, and guess what? I get velocity. So that's what happens when your first term is constant. But then if I want to do position at t is equal to 3 seconds, that's where it's 1/2 acceleration t squared. You know what I mean? And even that's kind of difficult for me to see visually, but when I do the integration, that's obviously what comes out. Negative 4.9, that's negative 9.8 divided by 2, t squared. That's position. And it's because this graph, your areas are a triangle. But even that, I'm kind of losing the connection between the calculus, and it's almost easier for me with energy equations where you have like, well, it goes back to be like, hey, if this is the velocity initial is 0, and then velocity at 3 seconds is negative 29.4. This is where this half comes up, because it's like, cool. Let's say you were driving 0 miles per hour to the next town. How long would it take you? Obviously you wouldn't get there at all. But if you're driving negative 29.4 miles, or just 60 miles an hour to the next town, it's 60 miles away, you'll get there in an hour. But if you decided, this is what's happening. If you decided to start at initial velocity of 0 miles per hour and then slowly over the entire course of that hour, slowly ramp up linearly to 60 miles per hour. So there you go. You're having a constant change in velocity. A change in velocity over a constant change in time is basically what gravity is. It's a constant. You're constantly changing your velocity over that same interval of time, and then you get a linear graph. So if that's the case, you have to say my average speed was 30 miles per hour for that entire trip. So even just right here, that's the nature of this triangle. The area of it is only half. So if you just thought, well, hell, I just want to position time is equal to 3 seconds. I just want to say that's equal to the velocity at t is equal to 3 seconds times time. You know what I mean? So now I would have 3 seconds times, what was the velocity at 3 seconds? Well, didn't we just easily say the velocity as a function of time is just the acceleration times t? So we've already done that, and it just seems, to me like, oh, well, easy peasy. If I know the velocity at time 3, shouldn't that be the position? No, but at least from just the guessing, just the get there perspective, it's a half. So if I did take this equation, velocity at t3, well, that's just the acceleration, 9.8 times 3 seconds. And now you'll see how you get seconds squared, because now we're just going to take it by another. So now this is my velocity term, and now, well, if my position is just that times 3 seconds, well, it would be if velocity was constant. If we were going 30 miles per hour the entire time, but we're not. We're going from 0 to a max, and so the average velocity is what you need, so that's where that half. So anytime in integration you see like 1/2, like 1/2 k change in x squared, you know what I mean? The spring constant, 1/2 mv squared. This is where that integral happens. And let me see if I can talk my way through this. Because if I did have this, if I said this, and this is the equation that you're getting from that. So if I did say, hey, this is the velocity, this would be the energy. So this would be kinetic energy. If this is the points of kinetic energy given every velocity, then how could I go the other? I don't know if that's going to be a good example for me. But even here's position. Position is in meters. What does it mean to go the other way, to differentiate? It says, well, I want to know the change in meters, per a change in time. So it's just like, hell yeah. So any kind of differentiation is usually with a change in time. You could do anything. You could say, I want to know a change in meters with a change in velocity. You know what I mean? You could do that representation. But just typically it's going to be a change in meters, change in time. And meters is x, so we're going to have a change in x, change in t, and therefore you have like a dx dt. And that's what you're trying to solve. But we do know that change in x, change in t, by definition, go back to the definition of velocity, that's change in position, change in time. So cool. Just taking an equation of position, now we know that, like, well, if this is my equation for position, what can I do? I can be like, well, I want to know position with respect to, I want a position divided by time, dx divided by dt, and that's going to give me velocity. Now you can't integrate position to get anything else, because, well, let's talk about this. If I integrated position, I would have, hey, 1 second here, and then position is like, so we already, in 1 second, you're going to go negative 4.9 meters. So now, what the hell does the area of this square, let's say it is linear, it's about, especially x squared is basically a triangle. So we're going to have 1/2 negative 4.9 meters times 1 second. Well, cool. We'll get negative 4.9 divided by 2. We're going to get negative 2.45. Now that's not the issue, but what the hell is a meter second? You know what I mean? Yeah, it's kind of a meaningless term at that point. You're just like, well, it's a physical representation. Like, don't get me wrong, it probably doesn't have any practical application. But actually, I don't know if it does. But it's just like that's kind of your limit, like going that direction. Now, if you go the other direction and say, and go, well, if I take position, which is in meters, how the hell do I go the other direction? Well, this is x, and then we can go dx dt. Cool, that's velocity. Once I get that, well, can I go change in velocity, change in time? Hell yeah, that's acceleration. And can I go change in acceleration, change in time? Hell yeah, that's jerk. And then can I go change in jerk, change in time? For sure, that's called snap. And then can I go change in snap, change in time? You can go as far as you want. It is going to be physical representations of how, the speed is changing, how the change in speed is changing, how the change in the speed is changing, how the change in the speed is changing. You know what I mean? So yeah, snap, and these are pretty good. Jerk and snap are pretty good representations of those parameters, and keeps going. You know what I mean? And if you have a function that's like, hey, my velocity is a function of sine of x, well, hell yeah, you can integrate this. You know what I mean? And what the hell does it mean to integrate? So let's say let's say this is theta, and I know my position is a function of my position is just sine theta. You know what I mean? And time's a constant, because the example that I would use, you're at a stop sign. What you would do is you would be at stop, and then you would drive down the street, get max speed, and then come to a stop at the other stop sign, instantly put it in reverse, and then go back the same. Have a max here, and then start to slow down. And basically what you're going to be doing is you're going to get a velocity curve of this. And obviously you're going to have a change in velocity, because your velocity is max at this point and is 0 at that point. You know what I mean? And so here actually is where you get no change in velocity, because velocity change in time, you take a small snippet of time of dt, well, hey, your velocity didn't change, it's flat. But here you get the most change in velocity. And if you keep going back and forth, you will have a sine curve. You know what I mean? Because you'll have, consider this the positive direction, and this is the negative direction. Alright, hell yeah. So now I think I have enough, mental imagery of drawing the squares, when I do the hand waving of the integration. And so hell yeah. And you know what I mean? Obviously, this is just a 5-minute problem. Equation 1 is Vx initial, t is equal to 10. Then we have acceleration. Now we'll just do it, just really simple. Yeah, so now this is just going to be V is 9.8. T, position, plus C though, and position is going to be, and even if you want to do it this way, and this is negative, but you can go negative 9.8, and this is C1, T plus C1T, plus C2. And then you can go back. So you already got your position equation, and you can go back and say, at t is 0, and this is in the y direction, because you have Vx initial, Vy initial, cool, and then that's your V initial. So Vy, so if t is 0, what is Vy? Well, it's just that it's just Vy initial. So our equation becomes Vy is negative 9.8 t plus Vy initial. This becomes Vy initial t, and then so we can do the same thing. At time is equal to t, at time is equal to 0. Oh, damn it. This is squared and this is divided by 2. Holy Toledo. And that's where it is good to go back to the, hey, this is t to the 0. When you integrate this, it goes t to the 1 plus 1 divided by 1 plus 1. You know what I mean? And so, and damn it, yeah. Anytime you make a mistake, might as well slow down. So acceleration is dv dt, negative 9.8. T to the 0, separate variables. dv is negative 9.8. T to the 0 dt. Integrate both sides, and we got v is equal to 9.8 t to the 0 plus 1 divided by 0 plus 1 plus a constant. And then we figured out that constant, so we got negative 9.8 t to the 1 plus v initial, vy initial. All right, hell yeah! So that's what we have right here. We know that this is d dx, and this is this is the y direction. Holy Toledo! Y in the positive, and this is x in the positive. So yeah, so we are going, instead of I'm glad I slowed down, because now we have velocity. Velocity as a function of y is dy dt. Okay, now we can put this. We can go dy dt is equal to negative 9.8 t to the 1. And yeah, there's no reason for me to, try to go fast. You know what I mean? I do it with a calculator. Just don't write anything down and see if you can just take your calculator and then solve the problem. That's usually how I do it, because the second you're writing, you're explaining to yourself, and you're explaining to others how you did things. And so why not just take the extra step and over-explain? Okay, so this is plus Vy initial. So now we can separate variables. So we're going to have something like dy is negative 9.8 t to the 1 plus Vy initial. And this is outside the brackets because, you can FOIL this through. Because you could just take the individual integral of negative 9.8 t to the 1 dt plus Vy initial dt, and then take separate integrals. So just other things, it's like, hell yeah, that you could be doing. And is this the definition of superposition? I mean, not superposition in the quantum sense, like, ooh, but just like, you know what I mean? Hey, if I'm adding those areas and getting this point, you know what I mean? And then I'm adding these areas and getting at this is 0, and at time 1 I'm getting that point. Well, these are going to add, and we're going to get that point. You know what I mean? So I think that's what this is. Because if these are integrals and you're finding the area 1 plus area 2, you know what I mean? If we're integrating from 0 to 1 second, you know what I mean? Hell yeah, those areas are additive, and then we'll go from integration from 1 to 2 seconds. You know what I mean? And you can just plot those points as well. So that's cool. Now, holy Toledo, am I freaking out of what an integral is? Because if we do take the integral, we're going to get an equation, basically that says, so we are going to integrate this. Because, yeah, I think I just got messed up, even just right there. Because negative 9.8 multiplied by some dt is the area. You know what I mean? So if I just say my dt is 1... oh no, yeah, that's right. That's the same situation we got into. So I'm glad I did this. Because here is my velocity term. So if I go velocity in meters per second times seconds, hey, guess what? I get meters. But because this graph is like this, it's a triangle, you know what I mean? I'm basically needing my average velocity. So, if I wanted an equation for the area under the curve at 1 second, I would need to divide this by 2 That's it. And then multiply by whatever. And that's exactly what happens. And that's where yeah. And that's where position is the second derivative of acceleration, dt squared, written like that. Okay, so I'm still not I can't do 100% tutorial on this, but I might as well go over the things that I want to go over. So cool. So let's integrate this, and because I guess my take-home point is once we do the hand-waving integral, we get an equation. And that equation specifically says at each of those points, and it'll be a negative one, but at each of those points, that is going to be my position. You know what I mean? Because I'm taking velocity times meters per second times seconds. So that is. So once I do the hand waving, I actually get an equation for position as a function of time. We're done. And then I can just evaluate it at each t is equal to 3 seconds or whatever. But before this point, if I just say, hey, before my integral, well, yes, it looks like I'm taking, part of the equation for velocity and then multiplying it by the change in time. You know what I mean? So there you go. But then just from realizing this isn't a constant, it says negative 9.8 t. Now this one's a constant, you know what I mean? So when we do the superposition, hell yeah, this velocity, this is in meters per second, and it's time to the 0, and I should have put that in there, and we wanted to find, like if that was just the case, if we just said, hey, we just have a constant velocity, and our velocity is positive, 7 meters per second, kind of with this basketball. And we want to know at t is equal to 3, what's our position? And that's all we had? Hell yeah. It would just be, our position would be meters per second times seconds, and it would just be 7 times 3. It would be 21 meters. But not if our velocity equation is like this. If our velocity equation is like this, no. And no, this is a good place to actually... Alright, this is a good place for, because I've always been talking about, hey, this is constant, and then if we do have a triangle, it's like that, but that's not what this equation says. This equation says, sure, like superposition. We do have a velocity as a function. Like velocity is there, so as a function of time. We throw in t, we get 3 times the velocity. We throw in 0, we get no velocity. But then it's saying, hey, it's times a constant. So, this is the v1 term, this is the v2 term, and then this is saying, hey, we have some sort of initial velocity vyi. So then superposition says, well, you're... oh, get more light. Alright, hell yeah. So yeah, superposition says you got to add these. So the actual graph, it looks like that velocity initial, and then plus. So this is the actual equation. And that makes sense because this part going through, and this is t to the 0, but hell yeah. So you have an equation, so this right here is very synonymous with y is equal to mx plus b. Your t is your value. This is your relationship. This side of the equation, 2 variables. That side of the equation. This is your slope of that line, and then this is where it hits the y-axis. And in this case, we hit a positive y-axis, but this equation says it's a negative. So there you go. So this is the actual equation of that. We have positive vyi, and we have a slope of over 1. Down negative 9.8. So even right here, you know what I mean? I can just draw it kind of to scale. We had initial velocity of 7, and then right off the bat, 7 minus 9.8. We're going to go down to, so if that's 7, another 7, this is negative 2. So at 1 second, we're already down to here. So that's going to be... that's going to be our graph. You know what I mean? And now I don't know if the superposition thing was actually a true statement at all. Well, I mean, was it? It was. I mean, it was just like, hey, no, it was. It was like, hey, this constant added to every point. Well, you gotta take this point up to there, and then you gotta take this point up to there. Now, this one's wrong, so let's do it again. So we're gonna have, and let's draw it to scale. So we have 1, and then we got like 9.8, 9.8. And then so this graph looks like this. And then the initial velocity looks like that. When we do the superposition, this pops up to there, and then this pops up just to there a little bit. And then this one pops up. If this is negative 9.8 and this is 7, this one pops up to that negative 2. So there you go. So you get this. Okay, so hell yeah. So now, I mean, it is just so useful. Like I said, the hand waving of integration just makes, you know, the basics, you know, what the hell are you even multiplying to get your areas, and what the areas even mean. I mean, they're not areas in the sense of meters times meters. They're in the sense of like, hey, if I take this variable and then multiply it by another variable. You know, if I take meters and multiply it, if I take meters per second and multiply it by seconds, well now we're taking two different things, but the product of those is a very useful something that we have a physical, tangible idea about, you know what I mean, of distance. And if we take acceleration, meters per second, obviously just a little bit more intangible to the average person that's not into physics, but we multiply that by second, hell yeah, we get a change in velocity. But yeah, from that perspective. Okay, so holy hell. So now where do we go? You know what I mean? Might as well write these equations just a little bit nicer. And I'm going to go print out another sheet of paper because we've just been rambling. Alright, hell yeah. So we have a fresh sheet of paper, and basically this is all we got, you know what I mean? We have an equation for velocity in the y as a function of t, and now we know that, well, acceleration, dv dt, or change in velocity, change in time, but now we know that velocity is change in position, change in time, and so, or dx dt, we know for vy, it's going to be change in y, change in t. That's the only thing that's kind of my biggest hiccup right now, just making sure that this is the velocity in the y direction. I'm just so used to doing it in the x. So let's do it. So now that this term becomes dy dt is equal to negative 9.8 t to the 1 plus vy initial, and you can do t to the 0 if it makes the integration easier. I'm just going to bring the dt over here, make life simpler, and then integrate. So now we're going to have y as a function of t is equal to, and then all the function of t means is just like, hell yeah, that's what we're left with. You know what I mean? We only have constants, and then t is our variable. So we're going to go negative 9.8 t to the 1 plus 1 divided by 1 plus 1 plus vy initial t to the 0 plus 1 divided by 0 plus 1. See, now you can't mess up the integration. So we got negative, and this is divided by 2, so now we got negative 4.9 t, that's squared, plus vy initial t to the 1, plus a constant. Now when we throw in time is equal to 0, hell yeah, our position is 2 meters. So c is equal to 2 meters, and now we finally have an equation for y as a function of t is negative 4.9 t squared plus vy initial t to the 1 plus 2. And so now, cool, but how do we relate, you know what I mean, this the time it takes the ball, the time it takes for this vertical to get to there, how do we relate that to what the hell's going on? Well, the parameter says, hey, this ball has to hit that basket at 3.05 meters. Okay, so now we do have something about position. We know that our position initial is 2 meters, and our position final is is y final is equal to 3.05. Now because you just have equations, these are your gold standards. So that's why integration is definitely the way to do it. And even in the physics book, you know what I mean? I've never understood why physics, after I didn't understand all the crazy equations that you were just supposed to like memorize or something, you know, were just simple calculus gets you there, plus, you know, because you always have this constant integration because you might be at a height, you might have initial velocity. And so I just never understood the first couple chapters in normal college physics, because you should already have an understanding of calculus at that point. And so why not just get the equations for position and then get the equation for velocity and then use them in useful ways? So we can actually find time, because when at time final, you know what I mean, it's synonymous with we're going to be at y final, you know what I mean? So whatever time final is, that's synonymous with 3.05 meters in this y. So we can do this. 3.05 is equal to negative 4.9 time final squared plus vy initial time final to the 1 plus 2. And the unit, all the units on this are in meters. But anyway, so there's an equation for time final. But how about this one? You know, we just threw this out there. What the hell does this mean? Well, this means, hey, our velocity times time. What the hell is time? Well, we're going to start at t is equal to 0. Some problems you might not. You know what I mean? Some problems I mean, because this right here is in. So let's do that. Let's do, because we could just. I'm like just having an aha moment that guess what? You know what I mean? What the hell is the acceleration in the x direction? You know what I mean? Because that's what we'd want to know. Well, we know that's 0. Okay. Well, what's the definition of acceleration? It's this, and so we can say dv dt. And this is 0 with respect to time is 0, and every other, you know, variable under the sun. Position, but time and position is 0. All we want to know about is time, so we have something like this. Now separate variables, and we got dv is equal to dt. This is the first time I've ever thought of this. Instead of being like, well, no, it's constant, and I know how to do, once I got a constant, I know how to do things. You know what I mean? But this just gives you that first equation that's linear. And then after that, well, like we said, this is position. So this is a position equation that's linear. And we said, what the hell is integrating? If this is position, you know what I mean, in meters. Oh, the TV is doing the, holy Toledo, emergency alert. Anyway, and then 1, 2, 3, 4 seconds. What the hell? And this is time in seconds. So this is 1, 2, 3. What the hell does it mean to take the area of this? And foreshadow, it's meaningless. I mean, I'll look it up. What the hell, meters? So we're going to have meters. You're going to have meters times seconds. You know what I mean? And so in integrating this is, kind of once you get to a position, so this is x, this is the x, x of t, position in this direction as a function of time, you can't integrate it no more, you know what I mean? So, okay, cool. But we can know that the acceleration is 0, and hell yeah, we can integrate 0. So that's what we're going to do. We're going to integrate dv dt. I'm sorry, I already messed up. We're going to integrate 0, 0 t to the, Yeah, holy Toledo. Maybe I don't know the actual, like, I'll have to research, like, what that would actually be, but we're going to integrate dv is equal to 0 dt and integrate that. Oh, perfect. It's no area. The area under that curve is no area. So when we integrate, we get v is equal to Alright, sorry about that. Had to take a little break. But hell yeah. So this side we get velocity of x, as a function of time, is equal to the integral of 0 is just 0. But it's 0 plus a constant. You know what I mean? So now yeah, because this is 0 times t to the 0. T to the 0 is 1, but you still have 1 times 0. So this thing is 0. And then when you integrate the area under the curve of 0, because we just said, here's my acceleration. There's my line for acceleration. It's 0. What the hell is the area under that curve? 0. Perfect. But what integration says is like, well, maybe at time 0, you do have some sort of velocity in the x direction, which we do. Imagine that. We don't have any acceleration at any time in the x direction at all, but we do have an initial. So when we throw in t is equal to 0, there's no place even to put the t is equal to 0, but at that time, velocity initial in the x direction, velocity in the x direction at t is equal to 0 is velocity x initial, and we do have that. So we're going to have velocity x initial is equal to c, and then booyah, so that solves it. So now our equation for velocity of x of t, velocity in the x direction as a function of time, is just vx initial. Now we can go to our second equation. You know what I mean? Velocity, change in position, change in time. So we can say that this is dx dt, and you can even write dx as a function of time. You know what I mean? Dt, and that's what vx as a function of time is. Vx as a function of time is the change in the position function of time divided by dt, and that's going to equal vx initial. Okay, so now we basically have something like this. Separate your variables. So we have dx of t is equal to vx initial dt. Now we can integrate. Integration of dx just becomes x. So now we have a position. We have a position function as a function of time. This goes to vx. And again, this is vx initial time to the 0. You know what I mean? It's not a function of time, but time to the 0. So when we do go to integrate, it's going to be t to the 0 plus 1 divided by 0 plus 1 plus c. All right, hell yeah. So now here's our equation for x of t. It is just going to be vx initial t. T to the 1, but we can just call it there. So we finally got it. You know what I mean? Hey, this vxi times t, which was just obvious, well, is a position function at any given t. We can throw any t in here and then find the position. So there you go. And it's t to the 1, but we'll just leave it at that. Well, let's do t to the 1. Even though sometimes that gets a little bit busy. You know what I mean? That's a little bit busy putting the 1 there. You might confuse it for something else. Okay, so hell yeah. So we do have an equation for x in that direction. So then we can do the same thing. When we hit 10 meters, when we have 10 meters on this side, that's going to equal vx initial time final. You know what I mean? So at time final, the same time it took the basketball, you know what I mean? This says due to this constant velocity, the basketball will reach this point in the x direction at this time final. That's the same time final that it will reach the y direction at 3.5. So all that was just to get, basically two equations that are related. So let's write this down. So position in the y is equal to negative 4.9 t squared plus vy initial t plus 2, and then x of t is equal to vx initial plus, t, that's it. And so again, we can write these things in. So we have 3.05, this is the y height, is equal to negative 4.9 t squared plus vy initial t plus 2. And then here, our distance at time final is going to be 10 meters is equal to vx t. And I guess I'll do final on this, you know what I mean? Because that's what... So now we have, and this is Vx initial. So now we have Vy initial and Vx initial. And what we wanted to find, at the end of the day, we wanted to find just the velocity initial. You know, not the x component, not the y component. So now we want to, make a relationship that says this is Vy initial, this is Vx initial, and this is V initial. And this is 40 degrees. And so we know that if this is the hypotenuse, we have, I guess the equation for this, Vx initial is equal to V initial cosine 40. If here's the angle, sun is shining, this is the sine component, this is the cosine component, the one we want. This is the hypotenuse, it's the bigger number. We're going to multiply by a number that's a fraction between 0 and 1. We're going to multiply by a fraction, obviously taking the bigger number, multiplying by a fraction to getting this component. Same thing, velocity y initial. V initial, sine 40. It's the vertical component, sun is shining on the vertical component in this case. If this was your angle, over here the sun is not shining on the vertical component. With this angle over here being 50, then this is your sine of 50. You know what I mean? So that just because usually your angle's like this on a horizontal, yeah, your sine component most always is going to be a vertical, but it doesn't have to be, especially if you take the sine of this angle. Sun is shining on that angle. This is the adjacent. This is the cosine of 50 portion. Okay, but what we have here is now we have an equation for x, Vx, and we can throw that in there and just get Vi. So cool. And then we can take this equation, throw it in there, and then we can get that in terms of Vi. So hell yeah, so let's do that. 3.5 is negative 4.9 t final squared plus, and then we're going to go Vi sine 40 t final plus 2. So even the t final, that's getting a little busy for me. We can just say, hey, t is, but I guess we'll stick with it. So we have 10 is equal to Vx initial t final. Oh, damn it. I'm sorry. We have to do this one. V initial cosine 40 and then time final. So now we have two equations, 1 and 2. It's got two unknowns. We have time final as one of the unknowns and the velocity initial. And what we want is velocity initial. And thank God this isn't, even though we have a squared here on time. I thought, because of this term, because we can just solve for time final straight up, Oh, no, I haven't solved this one all the way through. So anyway, so what we want to do is solve for VI right here. So we're going to go VI is equal to, no. At the end, we want to solve for VI. So we want to shove something into time final. Some of these are like, the magic trick is like, hey, I got two equations, two unknowns. What the hell do I want in the end? Well, I want velocity initial. So I need to change those things into velocity initial, right? So then to change those things, I have to get an equation as a function of time final. And I wish I just had this as time. The TF is getting too busy for me. But we're going to take this crap and then throw it downstairs. 10 divided by VI cosine 40. Hell yeah. Now I have an equation for time final. Now we're going to shove it into here and there. And yeah, good enough. So we're going to go 3.05 is equal to negative 4.9. and then we're going to square this. That's what I was thinking. I'm just going to square it right now. T final squared is, I'm just going to say 100, get done with it, and then VI squared, and then cosine. I'll put the squared right there. You know, you don't have to. You could definitely do this. This will probably make sense to most everyone. You know what I mean? And I would, you know, I would prefer if people did this. You know what I mean? I don't know. There's no confusion there. I'm taking cosine 40 and squaring it. I guess this is just getting used to. Okay. So hell yeah. So 4.9 times that. So it's 100 and then divided by V initial squared cosine squared 40. Okay, hell yeah. That was that part. Plus, now we have V initial sine 40, and then we got to shove this in. 10 divided by V initial cosine 40. Oh, hell yeah. This is what I was talking about, is that these V initials cancel. And so now the x, we don't have to use a quadratic formula. So that's hella awesome. And we can just do this one straight up. So we have sine 40 times 10 divided by cosine 40. And so I'm going to store that as x. And so now we can take x to the other side. So we got 3.05 minus that x term is equal to negative 4.9 100 v initial squared cosine squared 40. I want to do it this way. And then we're going to take, we have to get this this thing up there. So hell yeah, I guess we're just going to redo it again. So we have v initial squared is equal to negative 4.9 100 divided by 3.05 minus that x term, which is just whatever's remaining there, which is the tangent 40 times 10 tangent 40. You know what I mean? So we could do that. 10 tangent 40, and we'll go 10 tangent 40, and yeah, that's x. Cool. Hell yeah. So now we're there. We're there. And this is acceleration divided by 2. This was our distance squared. So, you know, this is another way to be like, well, what if I just wanted an equation, wanted to set this up again? Well, this is height final. Cool. This is distance, and this is tangent of the angle. You know what I mean? So right there, you know what I mean? And then we'll solve it though. We'll go v is the square root of negative 4.9 times 100. Now, we can't take the square root of a negative, right? No, hell no. That's the definition of imaginary. Okay, so hopefully this, and we got 10 tangent 40. Oh, are we? Yeah. So we got 3.05 minus that. I just want to do a check on reality. So, yeah, so obviously those minuses cancel, but that's a good thing to pay attention to. And we got 3.05 minus 10 tangent 40. Cool. And hell yeah, we're going to get our velocity initial. So we're going to go negative 4.9. Alright, so negative 4.9 times 100 divided by 3.05 minus 10 tangent 40. And then the square root of that. And hell yeah, we got a velocity of initial of 9.57 for this problem, meters per second. And we're going to see how that compares to what we thought. You know, we thought at 10 meters with a 1.5 second shot. Oh, and in this thing we didn't even solve for time final. So let's solve that, because Curry was shooting 1.5 seconds. And what were we thinking this person was going to be shooting? Curry was shooting with a higher arc with 1.5 seconds. So if this basketball player is shooting with a less arc, we should have a time that's less than that, right? So let's do that. So time final is just hell yeah. So this is, I'm going to store this as v. So this is our velocity initial straight up, just the actual velocity of the basketball. And we're going to go 10 divided by alpha v cosine 40. And we get time is 1.36 seconds. And does that make sense? Curry did a 1.5 second shot, but at 40. So now I want to go. What I want to do, well, this 10-meter problem. I wish the hell this said 7.24 meters. I wish this said 7.5 meters, because then you could compare it with on the line threes. You know what I mean? If there was a 3-point on the line, feet right there, it's 7.5 meters basically, and then you could easily compare this problem and see if anyone is shooting a 40-degree angle. But I can still do that. I can still record the times of problems and set this up for 7.5 meters. Because I have the equations, and so let's talk our way through that where we wouldn't even need Excel. So I want to know the angle, and I want an equation for the angle with an input of time, and then obviously the distance of 7.5 meters. You know what I mean? Whatever shoes, if the toes are on the 3-point line, well, it would be 7.24 meters. That's the actual NBA. But then I want those input parameters, and then I want to find the angle. You know what I mean? And I can get the time from YouTube. And so we might finish with that. And so the one thing that I did want to finish with at least is if this is my equation, velocity, and I do want to get it back to just something with letters. Well, this is going to be acceleration divided by 2 times d squared divided by height final minus 10 minus d tangent of holy, did we make an error here? Because why aren't we getting a function of 2? Did we? Yeah, it's like didn't we have? I think I missed something, because our equation. I'm glad I did this, because our velocity equation should have a component of the height initial, the y initial, and so this height final is just y final. So let's see if I ran into an error. So this is my equation. Oh, hell yeah, I ran into an error right here. You know what I mean? When I solved for time final, and then I started, chugging it in right there, yeah, I totally forgot about this plus 2. So then when I went over here, I go 3.05 minus 2 minus sine 40 times 10 divided by cosine 40. Oh, I'm glad I caught that error. And so now we're going to store that as alpha b. Now, that should be right, though. Oh, this got too busy on me. Oh, and you know what? I don't even think I ever did this cosine squared. Holy, so 2 errors there. So let's slow it down, and let's do that. So we have our equation, 3.05. This is why you should do less busy stuff. 4.9 t squared plus, and I'm just going to say this is v, you know what I mean? Just keep things hella simple, 40t plus 2. Because this was the definition of losing stuff. That t final, that totally messed me up. So a lot of the physics books say carry all your variables, because this would be a distance, all the way through. I disagree with that. I think that's a good way to go back and check your answer if you think your answer is wrong. But you should always know kind of your answers right, because you should be guessing. But even this, we got something fairly decent, and it is wrong. And so this one is going to be v cosine 40t. Cool, so there's our 2 equations. And so now we can put them together. So we can solve for t. T is 10 v cosine 40. So now t squared is 10 squared v squared cosine 40. And I'm going to do this, holy Toledo, because this will help me way more. And now we can throw it into there. So we got 3.05 is equal to negative 4.9 times 10 squared divided by v squared cosine 40 squared. Got it. Plus v sine 40 times 10 divided by, so now this is the t that goes in there, v cosine 40. Cool. V's cancel, and this is just tangent 10. So I'm just going to go tangent, tangent of 40. I'm sorry, tangent of 40. 10 tangent 40. Okay, now we got the plus 2. Cool. So now I have, I don't think I can simplify this anymore. So now over here, I think it would be nice to just get this positive over here. So let's go 4.9 10 squared v squared cosine 40. And I'm just doing this because and then we don't want to be walking on, we're kind of walking on eggshells to make sure we get this right 100%. Okay, so now, you know what I mean? Now I guess I want to go v squared up here, so I'm just going to do that. Sometimes it's just easy for me to, go v squared up there, take all this, and then put it right there. And so now I can rearrange the equation. I'm going to go v squared, but now I'm going to go 4.9. So doing these little tricks for me actually help me not mess up. Because else you're just going to be writing the same equation 1,000 times, and you're gonna just forget one thing. Cosine 40 squared. Cool. And then the square root of it is our velocity. So now let's do it. So we got, I'm just going to do this bottom part too. Cosine 40 squared. I'm going to even store that as x right now. You know what I mean? And then I'm going to go 10 tangent 40 minus 3.05. And then times x. Cool, so now we got the bottom part, and it's for sure even, so that's sweet. Now I'm going to store that as x. Now I'm going to go 10 squared, and then times 4.9, you know what I mean, and then divide by x. So I have made no mistakes, and now my velocity is 12.5. And now, for whatever reason, that makes more sense to me. Maybe it doesn't, you know what I mean? Maybe I'm just, if everything sounds like it makes sense, yeah. That's why physics is hard and sucks. So now, but now let's seriously go back and solve for t. So t is 10 divided by 12.5 cosine 40. So I'm going to store this as alpha v. So we have 10 divided by alpha v cosine 40. And we get a time of 1.044 seconds. So now this will be fascinating. I'm going to go and see if anyone is shooting a 3 in 1.044 seconds. I would think, oh, I better catch myself here, because I was just like, well, it doesn't seem physically possible, but we just set up the physics. The physics are what they are. If someone takes a 40-degree angle shot from the 3-point line. Well, no, this says 10 meters out, so that's why this is a little bit crazy, because it's farther than a 3 substantially, and it's a 40-degree shot, and the only way to do a 40-degree shot is to get a time of 1.044 seconds with a velocity of 12.5. So I am literally actually going to go back to Excel, because what we need to do is throw in the angle of 40 degrees right here, and then a distance of 10, and we want to, and we could have done that right off the bat, and then we want to vary our initial velocity. Oh, and I have to pause real fast, because this is the velocity in the y. This is the parameter that we use to set up our Excel graph, and that makes sense. And this was our input, maybe the velocity in the x, just because we want to know the time. But now that we solved this, we actually want to go back and say velocity in the x is equal to the velocity cosine 40, and velocity in the y is equal to velocity sine 40. So let's do that. So we got alpha v cosine 40, alpha v sine 40. And so there we go. So we have 9.578 meters per second in the x direction and 8.037 meters per second in the up direction. So it's very close to kind of what we were saying. We did 7.61 for Seth Curry's shot. So that's what we were comparing. For Seth Curry's shot, to get a time of 1.5 seconds, we needed, and this is at 10.10, what we thought was pretty close to 10 meters, put it that way. And we had an angle of 45 degrees. So a slopier angle. But honestly, we did think Seth Curry's shot could have been 9 meters. It could have been anywhere from 9 to 10.5 meters. We just weren't sure. But if it was 9 meters, hell yeah, we have a 50-degree angle. And it looked like a pretty, upward shot. But the main component here was the time. The time was 1.5 seconds. So you had to have a slopey shot if you're going from that. If my time is 1 second, well, you have to have a more arced shot. You don't have time to do a slopey shot. So that is fascinating. And so when I was saying, oh, it seems impossible to have what we got, no, that's not true. If we have a time of 1.044 seconds and we're shooting the basketball at a 40-degree angle, it's the only parameter. It's the only parameter that makes sense. That time being is the only thing that is physically possible. So what I'm going to do is go online and see if I can find any threes. And we'll just do this because I want to get one on the line so I know exactly where it is. But if there are some from downtown, I just know they're going to be, and I'm going to find more three-pointers online that are right at the line. And if I can find at least one that's under a second, you know what I mean, then I have something to compare, you know what I mean. Or I just want to find one that's at a 40-degree angle. That would be fascinating. And so what we're going to do is, so finally, we got our equation. So if we want velocity, initial, we're going to go acceleration divided by 2. That's that term. Our distance, and what should we call this? I'm just going to call it distance from the rim. I'm just going to call it d, and we're going to square it. So we got d squared divided by d tangent of our angle minus y final. Where the hell did our 2 go, though? Did we friggin' lose it again? Oh my goodness, I'm gonna kick myself. No crap. Like every time I feel like I don't think I lost it because I put it in somewhere. But from here we have over here we got 3.05 minus 2. Why the hell do I keep losing that part? And then we have minus holy Toledo. Or when I brought it back over here, I didn't add it in. Man, that's crazy. You know, that's when it's tough. I think I can do this real fast though. So we have 3.05 minus this 2, but also minus this 10 tangent 40. So there you go. And that's going to be equal to this, which is negative. So then I'm going to switch this over here and then create all this positive. So I'm going to have 10 plus 2, 10 tan plus 2 minus 3.05. That's the term I'm going to get. And then I'm going to get the velocity back up there, and then take that all downstairs. So I get all this, and then I get 10 tan plus 2. Holy, we didn't even do it right. You know what I mean? That's crazy making another error. But I'm getting really good at catching errors. You know what I mean? So that's what I'm kind of proud of. You know, see, it's like see if you can make errors and then catch them. And again, I'm going to do this 100%. We're going to go 10 tangent of 40 plus 2 minus 3.05 times times cosine 40 squared. Store that as x. 4.9 times 10 squared divided by x, square root of that. Yeah, I thought this was high, but you know what I mean? Just once you get the answer, you're like, I'm done. You know what I mean? Like, let's move on with life. But there you go. 6.67, 10.67 meters per second. That is going to change our time. And yeah, because that seems real fast. So now our time is going to be, we're going to store that as alpha v. Our time is 10 divided by alpha v cosine 40. And we got a time of 1.2 seconds. Holy Toledo. So time is 1.22 seconds. V is 10.67 meters per second. And what are these? These are alpha v cosine 40, alpha v sine 40. So these are 8.16 meters per second and 6.856 meters per second. There you go. So we have 1.2, and we were saying that, so yeah, we have a faster, no, we actually have a slower, a faster x component, a slower y component. So that's interesting than what we thought Seth Curry's was. Seth Curry's, we had a faster y component and then a slower x. And so that's just what you get when you have a steeper angle. And plus, this was a 1.5 second shot, and this was a 1.2 second shot. But again, the take-home point is if your shot is 1.22 seconds and your angle is 40, this is the only thing that will happen. You know, it'll go right in the bucket. Where Seth Curry, where we just weren't sure about the distance, but let's say we did dial it in at 10.5, that's what this was. We know the time was 1.4 seconds, and so we definitely know the angle. Angle was 46 degrees, let's say. Okay, so from here, we can actually do our letter equation. We have v is equal to the square root of acceleration divided by 2, distance squared, and then divided by distance, tangent of the angle, plus the initial height, y initial, minus the final height, and then cosine squared of the angle. And so that is how we get the velocity. And I do not know how to get an equation for angle. I do not know enough trigonometry to be like... But I am fascinated in learning more about trigonometry to be like, hell yeah, could I find an equation where I could just get it down to, the angle as a function of v, and then just equal something. Just an input into my calculator that I could do in Excel. Because then I would have exactly what I'm after. I would have an equation based on velocity. But actually I didn't want that. What I wanted was an equation based on time. So what I would do is come in with this v and say, hey, v is v is equal to vx initial divided by cosine 40, and then we know from our equation that the distance is equal to the distance was equal to vx initial, that initial velocity in the x direction, times time. And because velocity in the x direction is a constant, and so if we know the time, we know the distance. Meters per second times seconds is that distance. And then we would take this equation, and then we would want it in terms of velocity. So I would say this would be d is equal to v cosine 40t, and this is what I could throw in for every d, or I could, hey, every v is equal to d divided by cosine 40t. So that's probably what I would do, is I have a v here. I'm going to say this is equal to d cosine 40 times t. So now I would then I would take my time and figure out if I could do this with trigonomic identities and get a function that has input parameters of the distance, the initial height, the final height, and then the distance I want to shoot from. And it's going to be a function of time. So I go also to YouTube and figure out what the change in time for that shot was, what distance it was, and then I could even, from the basketball player, finagle with this height initial, whether the player was tall. But 2 meters for a player is pretty average. 1.8 meters is the average player. Look that up maybe, and then just a couple, you know what I mean. And so that's a pretty good estimate. But hell yeah. So I'm gonna go to YouTube and then at least get some. Alright, hell yeah. So I did it all in one page, you know what I mean, the 5-minute method. And then I actually found that it was really simple to get an equation for theta. So now we have an equation for theta with input parameters, that final height of the basket, that'll be unchanging. The height of the basketball player's arms, at the top of their jump or whatever. And then acceleration of gravity, that's unchanging, negative 9.8. And then we throw in the time from YouTube. And then we have the distance to the basket. But if it's right at the line, you know what I mean? This is unchanging. Basketball height's unchanging. 2 is a great parameter. Acceleration is unchanging. So basically, this is an equation that it's like, hey, go figure out from the three-point line how long it took that player to shoot the basket. And then you can plot, basically, you can get the angle of all the of the basketball. Now the only thing that would cause an error in that calculation is maybe the distance isn't exactly 7.24 regulation, you know what I mean? Because your toes are on the line, and where are you actually shooting from? I would say that's a pretty good, if the toes are on the line, hell yeah, because your hands are kind of out in front of you, I would say that distance is going to be pretty accurate. The only thing that might be not accurate is like, well, where in your shot are you taking it? Is this 2 meters going to be appropriate? You know what I mean? That would be fascinating. Kind of just look visually at a player's height, their stats, see where their head is, kind of measure up linearly from their head and see if where the basketball is within that, a tolerance of that 2 meters. It might not seem much, but hell yeah, these parameters definitely matter if you're trying to really dial it in. And so there you go. There's the framework. And you know what I mean? Should I start this problem, just for like, hey, just walk you through the steps? Is that how I want to start this video? Because we're going to end it by me going to YouTube and finding at least a couple different basketball players shooting from the three-point line. I kind of want to at least see one that makes this 40-degree angle. I want to see one that takes from a three-point. Well, again, now this isn't going to be representative because a 3-point 7.24, this is a 10-meter. So again, it's not going to be perfect to this problem just because I can't perfectly get 10 meters. But we know that the time is going to be less. I don't know how much less. I would say not too much less, but like definitely not 0.8 seconds. Maybe 0.9, but I just think it's not even under 1 second. I think from a three-pointer, my guess is that you can't shoot a three-pointer from the three-point line under 1 second. That would be a pretty good problem. Because could you shoot a three-pointer from the three-point line under 1 second? We'll find out. Okay, so now with further ado, because it is good practice for me to go through a whole problem in under like 5 minutes. So I'm going to try that right now. Alright, hell yeah. So we have physics, and we're going to do something we usually don't do. We're just going to go over this problem, hopefully in about 5 minutes. So we have a basketball player, shoots a basket 10 meters out. Now, a three-point line is 7.24. We'll go over that after this. So it's a far 3. And so anyway, 2 meters tall for the height of the throw, and 3.05 for the height of the basket. 40-degree angle, and then let's go for it. So typically these equations have like, you're looking for like a couple equations, couple unknowns, and continuity too. So we know that there is no gravity sideways. There's no forces on the basketball sideways. Velocity is constant in this direction. So our first equation right off the bat is if we knew the time it took from the throw to the basket, Well, that time times that velocity is 10 meters. So that's the first equation. Hell yeah. And then we know some components about we want to know this velocity. But we know, hey, this component Vx is that velocity cosine 40. You know what I mean? And so that's this equation. So that's technically the equation, one of the equations for our two equations, two unknowns. Now, the second equation comes from the fact that we do have some velocity up, but we have gravity, you know what I mean, sucking that right up. So acceleration is negative 9.8. What the hell is that? It's negative 9.8 meters per second. That's the change in velocity every second. So booyah. Within a fraction of a second, that it takes about a second to get here. Let's just say that. So in half a second, that velocity is gone, and then it goes back the other way. Okay. So but what we do is we integrate this. We know that a is dv dt. We separate variables. We integrate. So we get v is equal to negative 9.8 t plus, but we need a constant here. So you do this by putting in, at t is equal to 0, well, do we have velocity? Hell yeah, we have velocity. And it's that vy. And then you integrate again, because v is dy dt. Y is this case, you know what I mean? It's the distance in the vertical. And so we have dy dt. Separate variables, we'll have dy over here, and then throw the dt over there. Integrate, you get, you know what I mean, half the acceleration, t squared, plus that initial velocity times t, plus, you know what I mean, and here, you know what I mean, so at time is equal to 0, these go to 0. What's our height? It's 2 meters, you know what I mean, so we throw that in. Hell yeah, so that's our equation. And then we want continuity between these. So what we're going to do is pick the time t to get here. So at time t, that's t final, but I just call it t. So at that time t, well, we're going to go a distance of 10. So this equation is 10, and we got that v cosine 40 t. Now this equation, at t is equal to that t final, what's going to happen for y? It's going to go up, but then come back down to the 3.05. You know what I mean? So then you have that. And we basically have two equations. The two unknowns are t and v. But we just want the equation for v. So if you're smart, you turn this equation in a function of t and then jam it in there. And then you just got one equation with v. So that's what we do. We rearrange this. We get t is 10 divided by that v cosine 40. We also want to square it just because we have to toss this t into that square sign. And so we do square it. And then we just, you know, throw it in. So we have 3.05, 4.9, that t squared term, plus v, and we have sine 40, and then t, well, we have divided by a cosine 40, and divided by a v, and multiplied by 10. So we have v divided by v, those cancel. We have sine 40 divided by cosine 40, it just turns into tangent 40, and then multiplied by 10. So at the end of the day, this is just tangent, or 10 tan 40, 10 tan 40, plus 2. So these are constants. We get these to over there, so we got that. And now we have it equal to this. Our v squared is downstairs. You know what I mean? This is what we want. So we kind of do it all in one step. We take our v squared upstairs, and we take this, you know what I mean, and then we shove it within a parentheses right downstairs, right where that v squared was. And then we take the whole square root of it, and then we get something. V is the square root of all this. Cool. And now for our problem, you know, it's just numbers, but hell yeah. And so we get a velocity of 10.67 and a time of 1.22. So keep that in mind, because we have 10 meters out, it takes 1.22 seconds. We need a velocity of 10.67. Now that's meters per second. 10.67 times 2.25 gets us pretty close. 24 miles an hour for basketball. Now, what I wanted, I wasn't satisfied enough. I wanted to get this back into letters. So what we did is we said, well, negative 4.9 is just the acceleration divided by 2. That's negative 9.8 divided by 2. So we got a divided by 2. This 10 is this distance. So that's just distance away from the basket. And then this is our final height. And so we can get back down here. This is our final height right there. Minus our initial height, so y initial. Minus the distance again, tangent of the angle. And then cosine squared of the angle. Okay, hell yeah. So then now we have an equation for velocity. So at any given angle that I shoot, and knowing the distance away I'm at, I can know, and my height of shooting and the basket's height should be, for an NBA player, that shouldn't change too much. And this is identical. This might change how far you are, how big of a three you're shooting, and you get an equation for velocity. But this equation isn't the best because basically, I was doing this on YouTube, watching Stephen Curry shoot, threes, and what I noticed was like, hey, he's at the three-point line, and so I know from NBA that's 7.24. So we do something like this. We know that he's shooting at 7.24 meters. Because it's YouTube, I can clip it, and then I threw it into my video editing software and just really made sure the time was correct. And so I got like 1.06 seconds so at the three-pointer, the shortest time was 1.06 seconds with an angle of 42.2 degrees. But let's take a pause, because what I want was to get this in terms of just an equation for angle. I wanted to go to a YouTube video, and then, angle is what I want to know, but I want to go to the YouTube video, see how far they are away from the basket. Sometimes they're farther. And then know the time, and I can do that by clipping the YouTube, like I said. I know the acceleration, that doesn't change. And then typically the height of the basketball player and the height of those aren't going to change. NBA basketball players 1.83 meters on average, and then plus their arm height. So 2 meters is a pretty good estimate. Okay, hell yeah. So when we do this, we can clip videos of basketball players shooting threes, and I just did Stephen Curry for a few. Because I wasn't satisfied. And you'll see later in this video, I made a huge mistake. I clipped one clip from Curry, and the YouTube, I just went on YouTube, and then just saw how long the time was, and usually frame by frame, I thought was accurate. Hell no. And so I got a time of 1.5 seconds, and so that was wrong. That one came out, and when I put it into Wondershare as a normal video, it turned out to only be 1.1 second. And so even that long deep three had an angle of 37.6. But now I don't trust either of my YouTube. If YouTube I thought was accurate and said one thing, and YouTube should have been accurate, you know what I mean? Like you're watching a video in real time, hopefully it didn't get any weirdness. But then I clipped it, but yeah, so maybe these aren't right. But anyway, it's just like I'll have to do my due diligence later. But this video, I do my analysis on 1.5 second and then I said the shot was 10.5 meters, but 9.07 is more accurate, and we'll watch those clips. Because it's 6 feet away. I figure, hey, it looks like 6 feet away for that initial shot. But if the time frame is right at 1.1 second, it's 37.6. But if the time frame is wrong, we have this in our calculator, 9.07 and a time of 1.1. Whoa. Not 9.07. Why the hell is that messing up right now? No. Alright, hell yeah. And before I forget, how do we get this equation into an equation for angle? So the first thing we're going to do is like square V. Got it. But what is V? We go back to that equation, 10 times the velocity in the x direction times t. You know what I mean? And how do we get it in form of V? Well, it's 10 V cosine 40t. So we're going to just isolate the V. That's 10 divided by cosine theta t. We got to square it, so then we get that. And now this term, we can just substitute in. And we can see that this is d squared divided by cosine theta squared times time squared. And when we throw it in this side, the square root goes to the square, and we already squared it. Cool. We have a d squared and a d squared. Those cancel. We have a cosine squared theta and a cosine squared theta. Those cancel. So now we're just on a roll. We have 1 divided by t squared. So what I'm going to do is bring the t squared. What the hell do I do? Well, no, I guess I just go 1 divided by t squared. We have that area divided by 2, and then we have this. Now, to get closer to get this angle out, Let's see. Oh, I probably do this. Yep. So I bring this upstairs to the left, and then I bring this t squared up there. So hell yeah, I get to here, and then I rearrange. I add this d tan theta over there, and then I subtract this over here. Heck yeah. And then I just flip-flop the equation. That's what I do right there. And then I just divide by d. But all this in the parenthesis, now inverse tan is the angle. And now I have a function for the angle where I can just throw the distance away from the basket, the time it takes a shot to be made, and then the initial height of a basketball player, and then the height of the rim. Okay, hell yeah, let's get on with it. All right, we're back. It was just kind of getting bugged up in my calculator, but hell yeah, we got it all crispy. And so we have this equation, you know what I mean, and then we plug in those parameters. For that long 3, it was 37.6. So I think the take-home message is if you are farther out, you're probably going to do a shorter angle. After I was running, you'll see in the video, I was just not, I was thinking it was, is this problem wrong? Are most all threes taken from a 45 to a 50 degree angle? But my time was off. But like I said, I really don't know. I'll have to watch an NBA game and then actually clock some of the threes for me to be confident. Because even a recording, I just can't trust it. And I clipped it up. And the fact that I'm getting a different time just from YouTube and then clipping it out and putting it into a video editing software, that's the part that's not 100%. But at the end of the day, sure, people are shooting between 40 and 50 degrees, 40 and 48. So that's what I got. And if they're really close to the three-point line, here was the times, and I think the angles go up because you're probably shooting up over players. But anyway, like I'm hoping that this video editing software was a better time frame for that, because it shows the exact time frame. And so hopefully I'm right about these 42, 44, 45 for the actual arc length of a basketball. Else I'll just have to make this video over again, and we can do that. But hell yeah, so that's it. That's this problem in a nutshell. And now we're going to watch some of these clips. And yeah, you know what I mean? It's not the best, but we'll at least go through all those clips, all 4 of these in a row, this order, so then you can make your own assessments. But this first clip, I'll show you the mess up, and then I'll show this one. So I messed it up at 1.5, but anyway, you be the judge, and then we'll just go into the normal video. It's hella long because we learn a lot of stuff about integration, and we do it like we usually do it. But there you go. You know what I mean? That's the whole problem in a nutshell.
Brooks get him right back. And steps. Brooks get him right back. And steps. Clark came out nicely. Now the step back 3 is good. Tatum's 22, Brown 24, and both score. Turnovers now for Boston. Curry catches, fires, scores.
Michelle, and thanks for joining me. And hell yeah.